Batter hasn't even seen the pitcher let go of the ball, since the light carrying that information arrives at about the same time as the shockwave.
Yeah, the batter and pitcher are both gone, but that's not even the worst part of this. By popular demand, we are checking out XKCD's What If. Specifically, what if you swam in a spent fuel pool? Well, I'll tell you right now, there's no lifeguard on duty. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Love the disclaimer right here.
This question comes from Jonathan, who asks, what if I took a swim in a typical spent nuclear fuel pool? Would I need to dive to actually experience a fatal amount of radiation? How long could I safely stay at the surface?
Answer to the first question is yes, and you'd have to try pretty hard. And the second question, how strong of a swimmer are you?
The short answer is that, assuming you're a reasonably good swimmer, you could probably tread water anywhere from 10 to 40 hours. At that point, you'd black out from fatigue and
awesome, exactly.
Drown. This is also true for a pool without nuclear fuel at the bottom. And it's not really the question Jonathan was asking.
That really is the biggest hazard associated with the spent fuel pool. It's drowning. If you're doing work near the spent fuel pool, you need to wear a life vest for that reason. Right here, they're removing a gate. Though, interestingly enough, if you're on the refueling bridge above the core when it's opened up during an outage, you don't have to because you have railings. But again, the biggest hazard is going to be the water.
Spent fuel from nuclear reactors is indeed highly radioactive, and it's also hot. Water is good for both radiation shielding and for cooling, so fuel is stored at the bottom of pools for
Spent fuel is considered the highest level of radioactive waste, but it accounts for less than 1% of it by volume. Over 90% of it is low level and can be recycled. Things like the protective clothing these guys are wearing gets dirty, and they just need to do laundry. Intermediate level waste are things like filters in reactor coolant purification loops, things that regulate water chemistry which is the loop that regulates water chemistry in reactor systems. Those, it's a matter of have them sit for a few days so they can decay enough and then treat them in the advanced liquid processing system. You're mainly just going to have water. And that water is tested for both radiation and for chemical toxicity. And if it's good, then it can be discharged safely. But this is the high-level stuff that requires time in the spent fuel pool and eventually in dry cask storage.
Couple of decades until it's inert enough to be moved into dry casks.
Yeah, they got that right.
We haven't really agreed on where to put spent nuclear fuel yet.
Where we're at right now is they're stored safely on site, and these casks are immensely tough, can resist severe weather, even direct missile strikes, and their license is good for at least a century. And those licenses can always be extended. Other proposed solutions are in underground boreholes or caves that can be geologically stable for many thousands of years. So I don't know about us not being sure. I mean, we're more sure about this than we are about waste products from any other method of generating electricity. Even the vaunted clean sources such as wind and solar, people are struggling to recycle those materials.
One of these days we should probably figure that out.
Put up no swimming sign. There are actually no swimming signs near spent fuel pools.
But Jonathan asked about swimming in the pool. Here's the geometry of a typical fuel storage pool. The heat from the fuel wouldn't be a big problem. The water temperature in a fuel pool can in theory go as high as 50 degrees C, but in practice they're typically between 25 and 35 degrees.
Logs are taken on spent fuel pool temperature every day. It's usually right at 100 degrees Fahrenheit. And that geometry is pretty good. The plant I worked at, the fuel was 14 feet long, and the federal requirement in the United States is water has to be at least 23 feet above any radioactive source. And it was actually considerably higher than that where I worked. But that's a pretty good sketch.
Cooler than most pools, but cooler than a hot tub. But Jonathan asked specifically about the effects of radiation. For the kinds of radiation coming off of spent nuclear fuel, every 7 centimeters of water cuts the amount of radiation in half.
So let's back up a bit to what type of radiation is from spent fuel. The hazard is not the uranium. You can touch fresh fuel outside of water, not shielded from water. It's got cladding, and be 100% fine, because uranium is just an alpha emitter. Very short range. It will not penetrate the cladding of the fuel, which are typically made out of a zirconium alloy. So you're completely safe from uranium. One of my first jobs was actually to inspect some of the fresh fuel as it arrived on site. And all you wear are basic surgical gloves, and that's mainly just so you don't get the fuel cladding dirty. However, after fuel has been used in the nuclear power plant, the fission products are where the most dangerous levels of radioactivity come from. Things like strontium-90, cesium-137, iodine-131, and a whole bunch of other fission products that are typically beta and gamma emitters. That is what's going to give you a high dose of radiation. And that is what they're talking about in this video. So this halving in 7 centimeters, so the rule of thumb I'm used to for gammas is 5 centimeters. So this is actually being a bit conservative, but overall, so far they're doing pretty good.
Absorption means that 2 meters away from the fuel, there's a billionth as much radiation as directly adjacent to it, and 2 meters farther away than that, there is a billionth again as much.
You're getting very little dose unless you get very close to the assemblies.
The most highly radioactive fuel rods are those that are recently removed from a reactor. Based on the activity levels provided by Ontario Hydro in a report, these are the regions of danger and safety for fresh fuel rods.
All true. Fresh fuel is not only the most radioactive, it's also the hottest. And the reason for that is just radioactive decay. The spent fuel fission products decay over time, so radiation and temperature levels will go down. That's not the only factor, is the freshest. At the plant that I worked at, not every fuel assembly is single use. Some go into the reactor for multiple cycles. A cycle is a refueling period, typically 18 to 24 months. And in every cycle, there is a mix between fresh fuel, never been used, once burned, and twice burned. And the reason why you mix it up is to both optimize fuel efficiency and power distribution. It's important to have a relatively uniform power distribution in the core. You don't want any localized hotspots. It can just throw everything off. It's a bit like playing a game of Scrabble in how you arrange these fuel assemblies. But the most dangerous source would not only be fresh, it would also be a twice burned source, so it would have the most amount of fission products, and it would be at the highest enrichment level. Highest enrichment means more fissions also means more fission products. So be sure to look at your core map next time you want to go diving in a spent fuel pool.
Swimming to the bottom, touching your elbows to a fresh fuel canister, and then immediately swimming back up could be enough to kill you. Yet,
potentially. Though it would be very difficult to actually do. Because, assuming no one tried to stop your crazy plan, fuel assemblies are housed in these little grooves to protect them. So you're at a very disadvantaged position, geometrically speaking, in order to absorb that much dose, because you can't really get through to them. The top of the fuel assemblies are not at the tip of those racks. It's still a few feet below them. And even if they were just a few centimeters away, the amount of dose drops off rapidly. And you're not even getting the full brunt of the dose because the fuel is in protective cladding too. So good luck with this crazy plan.
Outside the safe dose boundary, you could swim around as long as you wanted. The dose from the rods would be less than the normal background dose of radiation you get from cosmic rays and stuff walking around.
True.
In fact, as long as you were underwater, you'd be shielded from most of that normal background dose as well. So you might receive a lower dose of radiation treading water in a spent fuel pool than walking around on the street.
That's a good point. Now, background radiation varies so widely depending on where you are in the world and where the biggest source of radon is, and that just comes from the Earth, from minerals, from the decay of natural uranium and thorium, which you would get more dose from that than you would from the sun or cosmic rays.
At least in theory. If there's corrosion in the spent fuel rod casings, there might be some fission products in the water.
I certainly hope not. There are program engineers with corrosion control programs. There's one specifically for spent fuel. There's an entire overarching spent fuel management program that looks at these sort of trends and identifies any defects way ahead of time. If there were corrosion or damage, it's actually possible to reconstitute fuel. Just think of it as putting a bundle of sticks back together with the highest level of oversight and regulatory bodies you have ever seen for such a task. This would all be done remotely, using cranes, possibly drones, depending on the extent of the damage, and the operators, the closest they would get would be the surface, just like those two stick figures. It's a very weird situation where you would put divers in the spent fuel pool. I've never seen it at my plant.
Spent fuel facilities generally do a pretty good job of keeping the water clean, but it's radioactive enough that it wouldn't be legal to sell it as bottled water. Which is too bad, because that'd be an amazing energy drink.
It's also highly acidic. Spent fuel pool water has very large amounts of boric acid in there, about 2,800 parts per million. And what boric acid does, think of it as liquid control rods. The boron in the boric acid shuts down fission reactions. So it's already impossible to have a fission reaction in a spent fuel pool because the geometry just doesn't work. The fuel assemblies are placed in a configuration that it's impossible for them to start up. But for good measure, highly borated water is used. And to get a sense of how big 2800 is in terms of reactivity control, at the beginning of a fuel cycle, a pressurized water reactor has a concentration of around 1300 or 1400 parts per million. This is giving additional shutdown margin, which is a way of saying we're not even close to beginning to remotely think about turning the spent fuel pool into a nuclear reactor.
We know spent fuel pools can be safe-ish to swim in because they're routinely serviced by human divers.
No, not where I worked. Remote monitoring equipment and crane operators at the surface.
However, these divers do have to be careful. On August 31st, 2010, a diver was servicing the spent fuel pool at the Leibstadt nuclear reactor in Switzerland. He spotted an unidentified length of tubing at the bottom of the pool and asked his supervisor what to do. He was told to put it in his tool basket.
If that supervisor worked for me, I would fire him immediately. So, Radiological Safety 101 here. Stay within your defined zone of what you briefed for. This was clearly beyond the scope of his work zone. Do not grab any foreign objects that you're not sure what level of radioactivity it is, because you don't survey the bottom of these, because no one goes in there. You survey the surroundings and you extrapolate, but no, you're not going to send divers in here to retrieve stuff without the highest level of radiological briefings to occur, as well as just basic water safety briefings.
Which he did. Due to bubble noise in the pool, he didn't hear his radiation alarm. When the tool basket was lifted toward the surface, the room's radiation alarms went off.
You would also have multiple radiation alarms on multiple parts of the body, because if you're getting that close to any radiation sources, the dose to your left arm could be that much different from your dose to your right leg, for instance. So you would be quite heavily monitored. There would even be some radiation protection personnel that you would call out to. They would be monitoring your position in real time because your radiation monitors will also act as a tracking device and they're measuring the dose for you. This is insane.
The basket was dropped back down and the diver left the pool. The diver's dosimeter badges showed that he received a higher than normal whole body dose of radiation, and the dose in his right hand was extremely high.
Which is why you have those individual body part dosimeters.
The object turned out to be a piece of protective tubing from a radiation monitor in the reactor core, made highly radioactive by neutron flux. The tubing in question had been...
So neutron flux, neutron can activate certain types of materials, usually metals. And by activate, I mean neutrons bombard these metals and turn them into radioactive material. Neutron flux is only a hazard in an operating nuclear reactor, though. You're not going to receive that by swimming near the spent fuel.
It was assembled in 2006, but a piece accidentally broke off and sank to a remote corner of the pool floor, where it sat unnoticed for 4 years. The tubing was so radioactive.
That's also staggering for something like that to go unnoticed for 4 years. Spent fuel pool is the highest level of foreign material exclusion, or FME zone. It is constantly monitored by cameras and has FME monitors to ensure, basically people that ensure no foreign material enters this area. If you're going to work above a spent fuel pool, the FME monitor has to log all of the tools, all of the equipment that they are wearing and using, and everything is logged on a list So after you finish work, they check again and make sure you brought everything with you. And that's because spent fuel is considered sensitive equipment. You don't want to have anything that can go in there that could possibly damage the fuel. Now, it's pretty robust, as in you would have to try to damage spent fuel, but we are not taking any chances at all. So that's why it is under the highest level of administrative controls. And there's a whole bunch of tools that are strictly prohibited for use in the area. One of them is tie wraps, because they're that easy to lose. And every tool has to be tied off to your body with a lanyard, has to be able to float, or they just don't let you in there. They even require you to put duct tape over the zippers in your protective clothing so the zipper doesn't fall in. So this was quite the cascading failure right here.
That if the diver had tucked it into a tool belt or shoulder bag close to his body, he could have been killed. As it was,
That's
the water
insane.
protected him, and only his hand, which is a body part more resistant to radiation than the delicate internal organs, received a heavy dose. So as far as swimming,
It's still possible to lose a limb. So all those silly things you see about growing extra limbs from extreme dose, you're more likely to lose one.
safety goes, the bottom line is that you'd probably be okay as long as you didn't dive to the bottom or pick up anything strange or drink too much of the water.
The real hazard is, again, the F-me hazard of if you were to just jump in a spent fuel pool and bits and pieces of your clothes, your watch, jewelry, necklaces, whatever you happen to have in your pockets could fall in, risk interfering with the fuel. That is probably the biggest hazard overall, and it isn't to the person. Second biggest hazard would be drowning.
But just to be sure, I got in touch with a friend of mine who works at a research reactor and asked him what he thought would happen to you if you tried to swim in their radiation containment pool. In our reactor? He thought about it for a moment. You'd die pretty quickly before reaching the water from gunshot wounds.
Wow, that's pretty intense for a research reactor, having armed guards. I mean, that's normal in a commercial nuclear power plant, but I guess at their research facility, they took safeguards pretty seriously in terms of bad guys getting their hands on radioactive material. Now, the two research reactors I went to, they didn't have any armed personnel. But then again, that was quite a long time ago. That was overall pretty good explanation. Still can't believe that one story, though. That would never fly anywhere I've ever worked, about a guy diving and picking up things on the bottom of the pool by hand. But yes, you would be a lot safer than most people think. By popular demand, we're going to check out what a nuclear submarine work is a spaceship. Good luck getting that thing into space. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's check this out.
This question comes from Jason, who asks, how long could a nuclear submarine last in orbit? The answer is not very long.
Yeah, I was going to say it's not really designed for orbital flight. You're designed to go the other direction with those, man.
But not for the reason I expected. The submarine wouldn't burst. Submarine hulls are strong enough to withstand 50 to 80 atmospheres of external pressure from water, so they'd have no problem containing 1 internal atmosphere of pressure from the air. And the hull would likely be reasonably airtight. Although watertight seals don't necessarily hold back air, the fact that water can't find a way through the hull under 50 atmospheres of pressure suggests that when the sub is in space, air won't escape quickly.
So this sort of thing comes up with any sort of leak check. I mean, let's face it, nothing has perfectly zero leakage, completely perfect seals. I remember this came up at the nuclear plant that I worked at. We had our emergency diesel generators are designed to be completely sealed in just to ensure that the room doesn't flood. After all, having water near your emergency diesels, well, we saw what happened with Fukushima, and that's not a good place to be. But you can't have actually zero leakage, but it's a very, very small number. That's less than like 1 drip per day is what it would figure out to. But I know there's different design criteria for designing something to go underwater versus designing something to go into space. Different sort of tests are done, different types of leak checks, but that is true that you're not going to have a bit different criteria. And I'm seeing this note here, there may be a few specialized one-way check valves which would let air out, but let's assume they can be closed. I mean, theoretically, you can solve something that can be closed, but again, nothing has leak that's entirely zero. The reactor containment building isn't 100% leaks. Now, those leak numbers are even smaller than that. I remember doing an integrated leak rate test during a refueling outage for a reactor containment building. And this is when we actually raised pressure, so up to about 9 psi. Now that's 9 psi gauge, so that figures out to a little over an atmosphere and a half inside. And that's a lot for something this big. Note how small the cars are. And acceptance criteria for something that big, don't remember it off the top of my head, but it's usually something like less than 1% of air volume during a 24-hour pressurized integrated leak rate test, which is a lot. And at that pressure, all the isolation, that is far above where all the isolation valves close. And many containment penetrations use double valve isolation.
Dangerous carbon dioxide buildup wouldn't be an issue, as submarines use CO2 scrubbers that can be run indefinitely as long as they have power. But oxygen is another story.
And if it's nuclear powered, nuclear submarines can last 20 years without refueling. And when I say refueling, I mean you're not actually going to refuel the thing, since 20 years exceeds the lifetime of the boat. Aircraft carriers will get refueled maybe once, but subs typically no.
Nuclear submarines use electricity to extract oxygen from water. In space, there's no water, so they wouldn't be able to manufacture more air.
Yeah.
They carry enough oxygen in reserve to survive for a few days at least, but eventually they'd be in trouble. The really big
How long is this voyage in space supposed to last?
problem, though, would be overheating, because space is so much warmer than the ocean. If you're pedantic, that's not really true. Space is, of course, very cold. But if you're even more pedantic, and I am, it is true in two different ways. Space
Well, there's no heat transfer, is what he's getting at.
in Earth orbit seems cold because it's so empty. Without a warm environment around you radiating heat back to you, you lose heat by radiation much faster than normal. But space in Earth orbit is actually warm. The pedantic reason for this is that temperature is a measure of the average kinetic energy of a collection of particles. And in space near the Earth, molecules can have average kinetic energies in the thousands of degrees.
This is especially true if, like, it's within line of sight of the sun. If it's when it's orbiting, like, behind the Earth, relative to that, it can get relatively cold. I know that's one concern that, like, astronauts that are doing spacewalks on the International Space Station have to take into account is, are you in direct sunlight or not? And then they can calculate how much time they can stay. So presumably this subcrew would have to do something similar.
This doesn't make space feel warm, though. When I was a kid, I remember watching my dad use a metal grinder. Whenever metal touched the grinding wheel, sparks flew everywhere, sometimes falling in a shower on his hands and clothes. I couldn't understand why they didn't hurt him. After all, the glowing sparks were several thousand degrees. I later learned that the reason the sparks didn't hurt him was that they were tiny. The heat they carried could be absorbed into the body without warming anything more than a tiny patch of skin.
That same logic is why you have fusion power plants that are in the hundreds of millions of degrees, some even into single-digit billions, such as the Z machine, but it's not melting all of the steel and metals or igniting all the piece of papers in the room next over. One, I mean, it's granted it's in a containment structure, but still, it's relatively small on a macroscopic scale.
The hot molecules in space are like the sparks in my dad's machine shop. They might be hot or cold, but they're so small and there are so few of them, they don't change your temperature very much. Instead, your heat...
And he mentioned radiation. That's going to be the main, like, radiative heat transfer, because there's not really much to conduct or convect because there's so little density. These molecules are just tiny. There's nothing like touching them, not going to do anything. Convection is not going to do much. It's mainly going to be thermal radiation from the sun, as far as a heat source.
Heating and cooling is dominated by how much heat you produce and how quickly it pours out of you into the void. And this is the practical reason that space is warm. Without air or water around you to carry heat away from your surface, you don't lose heat by conduction or convection, just radiation, which often isn't a very effective way to cool down.
Radiation is extremely inefficient method of heat transfer. I remember in some of my safety analysis classes, the instructor said, if you're concerned about radiation-based heat transfer in the reactor, then your reactor has already melted down to the point where conduction and convection pretty much did its job. So you're going to need those kind of crazy high temperatures for it to be a concern. So in other words, it's already game over at that point.
For most human-carrying spacecraft, the big problem isn't staying warm, it's keeping cool. And a nuclear submarine isn't just carrying humans, it's carrying a 200 megawatt nuclear reactor. It's hard to get good numbers on the efficiency of nuclear reactors in military submarines, but a conservative guess based on civilian reactors is that around half the reactor's energy, or around 100 megawatts, is lost as heat.
That's generous. Try 2/3 of it. And that's a bit more realistic. Now the one thing is submarines, they typically don't sit at 100% power like commercial nuclear power plants unless they're doing some sort of maneuver. But they can sit in like 30 or something like that, which you'd never see in commercial nuclear power plants. So you might not have 100 megawatts of waste heat, but you could still have on the order of 30, 40, 50 megawatts, depending on what power level this submarine is sitting at. Now in space, they could probably sit pretty low, but that's still a big heat source. To give you a sense of how big 1 megawatt is, that's about 1,000 times more heat coming from your microwave at home. And you're dealing with tens of megawatts at this point.
This heat is normally dissipated by seawater, but again, no water in space. Without cooling, a 200 megawatt nuclear reactor outputs enough heat to warm the entire submarine by about half a degree Celsius every minute.
Now, a lot of that will be accommodated by the reactor coolant system, though. So as long as you can have a stable loop, but the problem is there's no external source, so it's really, you're not going to necessarily get to that 0.5 degrees Celsius per minute immediately, is what I'm saying, but you will eventually once you heat up the coolant, and that's when bad things start to happen, as far as reactor control is concerned, if you don't have any big heat sink.
The submarine would become too hot for human survivability within an hour. But the nuclear reactor isn't designed to warm the submarine in this way, so instead the heat would build up within the reactor and lead to a meltdown. It appears keeping a nuclear submarine in orbit is...
I mean, you're removing your heat sink. Reactor coolant essentially has nowhere to go. Now, I disagree that it would happen within an hour because you're going to start off based on a lower power level, and you're going to have to wait for the reactor coolant to evaporate. It is going to cool it, even though it's not going to cool out to seawater, so it is eventually going to heat up, but you're going to have a few hours. But you will have considerably less time compared to, say, a commercial nuclear power plant when it loses its external heat sink. On there, you're going to have potentially a few days. And there's so many alternate sources for an external heat sink for a commercial nuclear power plant, whether it be additional sources of water or additional sources of piping, ways of moving the water to the reactor coolant system if for whatever reason several of them were to fail. Several additional modifications were put in for that after Fukushima within every plant in the US, including the ability to bring in external piping sources and external generators to run all of this additional equipment from a satellite location, and these can be brought in by helicopter if necessary.
It's a bad idea. But to get out of orbit, the submarine would need to slow down enough that it hit the atmosphere, which would slow it down the rest of the way. Without rockets, it has no way to do this.
Yeah, you'd be... That was an interesting idea, having nuclear reactors in Spaceship, but it'd be more like an RTG, not really a reactor in the traditional sense of the word, but like a propulsion system, such as the ones used on the Voyager probes. And this thing works completely differently than a nuclear reactor. It's a lot simpler. It just uses decay heat from radioactive materials to generate electricity. The source is typically something like plutonium-238, and it releases heat. The heat is converted to electricity using thermocouples, and this electricity is used to power a probe. Now, that's not going to be nearly enough power to run your nuclear submarine, but you're in space, so you're normally not going to put something like that in space. You're going to put something that uses very little energy but lasts a very long time. So it's designed for small things like space probes and on Earth remote instruments. Though there have been the cases of orphan sources with these. You can also use something like strontium-90 for this, but that's beta decay instead of alpha decay, which means if it is found by someone unaware, they don't know what this is, then it's more likely to become a hazard through that decay mode that is more penetrative and that also happens to be more radioactive. I'll pin a comment down below with a link to a video that describes what happens when one of these turns into an orphan source.
Okay, technically the submarine does have rockets. The problem is they're not attached to the submarine.
Really? That threw me off. I didn't think he was going to go this way. And yeah, I mean, some submarines do have those. They're called boomer subs. I don't think there's an equivalent called a zoomer sub, but I guess you can call fast attack sub zoomer subs. Please, someone in the Navy, tell me I'm wrong about that in the comments. I really hope I'm wrong about that.
Launching the missiles won't meaningfully propel the sub, but they don't need to be attached. They just need to be turned around. If the ballistic missiles carried by
turn around, so it's going to be banging up against the other side of the hull. Wow.
Nuclear submarine were placed in the tubes backward, they could each change a large nuclear submarine's speed by about 4 meters per.
I'm just picturing the thing like going down and then suddenly, because no restraint is, it just slides across to the side and like hits someone in the face. Man.
Per second. A typical deorbiting maneuver requires in the neighborhood of 100 meters per second speed change, which means.
So did they do this to get this thing in orbit? I think I missed that part.
That the 24 Trident missiles carried by an Ohio-class submarine could be just enough to get it out of orbit. Now, because the submarine has no heat-dissipating ablative tiles, and because it's not aerodynamically stable at hypersonic velocities, it would inevitably tumble and break up in the atmosphere. The debris.
Man, that would be a hazard. A broken nuclear reactor in space, now basically deorbiting, scattering a bunch of spent fuel, and it's going to be scattered across a wide area at this point. This would be a bigger radiological hazard. Now, granted, a lot of the fission products will burn up in the atmosphere, but still, I would say this is a bigger hazard, a way bigger hazard than a nuclear submarine sinking to the bottom of the ocean. Because even if the core uncovered and the core somehow fell out of the sub onto the ocean floor, you have basically a nigh infinite heat sink in the form of the ocean that is going to keep the core very well covered. Because that's basically what safety injection systems do in nuclear power plants, is they're designed to keep the core covered in water so it doesn't heat up and melt the fuel. So, yeah. This would be a lot worse of a hazard than simply a nuclear sub that sank to the bottom of the ocean.
Disintegrating in the air or plowing into the ground at several hundred knots. If you tucked yourself into the right crevice in the submarine and were strapped into an acceleration couch, there is a tiny, tiny, tiny chance you could survive the.
Really? I mean, that might be possible. Maybe if you had this sort of setup attached to your sub and it somehow survived and you jumped at the right height. Maybe.
Rapid deceleration into the atmosphere. Then you'd need to jump out of the wreckage with a parachute before it hit the ground.
Who's designing these sub? Yeah. So basically you're going to have to put a bunch of non-standard features into your submarine in order to have something like this even remotely possible, which you're basically better off just designing a spacecraft.
If you ever try this, I have one piece of advice that is absolutely critical. Remember to disable the detonators on the missiles.
Yeah, you don't want, say, a fire to inadvertently cause electrical switches to arm things. There's actually a procedure if you have to evacuate the control room of a nuclear power plant that you not only turn a lot of systems off, you actually disable them. Because the only reason why you would evacuate the control room is if there's a fire in the control room or if there's a fire in one of the adjacent relay rooms. And if there's a fire in the relay room, that could potentially mess with some of the controls. So you disable them to make sure the fire doesn't mess with your controls before heading to your auxiliary shutdown panel and switchgear rooms where all systems, basically all the control room operators, would operate everything from those auxiliary control rooms, and everything else that isn't in those rooms would be operated locally and manually. It's a scenario that is well trained for, but we hope we never have to implement because that can be a pain. And you lack that whole central command and control structure because you have to basically talk to people in multiple areas, and it's difficult to visualize the big picture plant status. Doable? Yes. Safe? Yes. Is it a pain? Yes. What if the Earth suddenly stopped spinning? Well, considering the Earth spins at about 1,600 kilometers per hour at the equator, things are going to go flying. And as heavily fortified as nuclear power plants are, they're not going to make it. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't think so. Everything there is nuclear, but I can certainly share some knowledge. Let's check this out.
This is a question from Andrew, who asks, what would happen if the Earth and all terrestrial objects suddenly stopped spinning, but the atmosphere retained its velocity?
Okay, so we're not losing the atmosphere. So if you're keeping the atmosphere, well, you're going to have a bunch of violent storms and a bunch of the particulate matter that's flying at supersonic speed is going to be entangled in said atmosphere. Take a robust atmosphere to somehow maintain it. We're entirely in the realm of magic at this point, so why not?
Well, first nearly everyone would die. Then things would get interesting. At the equator, the Earth's
Cool geophysics. Gotta love it.
surface is moving at about 470 meters per second, a little over 1,000 miles an hour, relative to its axis. If the Earth stops and the air doesn't, the air there will suddenly be moving over the surface at 470 meters per second.
So to give you a sense of scale, this is over 7 times faster wind than the strongest hurricanes. So I know there are certain buildings and even fortified structures such as nuclear power plants, their containment domes that are designed to be able to withstand sustained Category 5 winds, but there we're talking like 150 miles per hour, 155 miles per hour. So don't think they can stand up to this very well. Especially considering suddenly stop. There's going to be a massive acceleration at this. It would be one thing if it was a gradual stop, but considering the massive deceleration at work here from this relative velocity, it's going to be crazy.
For reference, supersonic speed is 343 meters per second. The wind would be highest at the equator, but everyone and everything living between 42 degrees north and 42 degrees south, which includes about 85% of the world's population, would also experience sudden supersonic winds. The high winds would only last for a few minutes near the surface before friction with the ground slowed them down. However, those few minutes would be long enough to reduce virtually all human structures to ruins.
Yep. This is just way too fast, way too much. It would be interesting if it was more of a gradual deceleration. Then I suppose it would be the long, painful destruction of the seas migrating to the poles and the atmosphere migrating to, though I guess in this case the atmosphere is staying the same, so forget that last part. Here, nah, too quick.
Even structures strong enough to survive the winds themselves would be in trouble. As comedian Ron White said about hurricanes, it's not that the wind is blowing, it's what the wind is blowing. Say you're in a massive bunker made out of some material which can withstand 1,000-mile-per-hour winds. That's good, and you'd be fine.
Good luck finding one that's strong. I mean, the only way would be is if it would have to be underground. Significantly underground at that point.
Fine if you were the only one with a bunker. Unfortunately, you probably have neighbors, and if the neighbor upwind of you has a less well-anchored bunker, your bunker will have to withstand a supersonic impact by their bunker.
And that's what's going to get you in, say, a hurricane, a tornado. It's more of the stuff that it's going to hit you with that will get you. It's not a matter of that you see in movies, as long as you don't touch the funnel cloud, you're fine. No, you're likely to get hit by something else. And at that speed, the something else doesn't have to be very big to cause severe damage.
My home in Boston is far enough north to be just barely outside the supersonic wind zone, but the winds here would still be twice as strong as those in the most powerful real-world tornado.
No longer supersonic, so just going to be extremely heavy wind, no shock wave. Though 330 is pretty close. Temperature and height variations could have some effects.
Buildings would still be smashed flat, torn from their foundations, and sent tumbling across the landscape. Winds would be lower near the poles, but no human cities are far enough from the equator to escape devastation. The highest latitude city on the planet is on the island of Svalbard in Norway, and even it would experience winds equal to those in the planet's current strongest tropical cyclones. Even so, the human race wouldn't go extinct. True, very few people above the surface would survive.
Not immediately, anyways, but let's see if he talks about the long-term effects.
The flying debris would pulverize almost everything. However, a lot of people below the surface of the ground would survive the initial event just fine.
The initial event,
There would be other lucky survivors, like the scientists and staff at the Amundsen Scott Research Station at the South Pole. The surface of the Earth at the South Pole isn't moving relative to the Earth's axis because it's on the axis. People there would simply lose contact with the outside world. They'd probably be confused until someone noticed that the sun had stopped moving across the sky.
The one thing I'm curious about is at the poles, so you're having a lot more wind, and we're keeping the atmosphere, so the wind could bring in some warmer currents to create some intense storms. Now, I do completely agree with what he's saying about whatever extreme wind conditions and storm conditions are going to be less so at the poles than anywhere away from the poles, but I don't think the poles would be completely unaffected even within a few seconds to minutes.
Then they'd be really confused. Back at the equator, things would get really weird. Winds sweeping over the oceans would have been churning up and atomizing the surface layer of the water. For a while, the ocean would cease to have a surface at all. It would be impossible to tell where the spray ended and the sea began. As the energy of the blasting wind...
Yeah, because you got these shockwave, these supersonic effects. I didn't even think about that. That's just cool.
Began to dissipate, it would mostly go into heat. A lot of heat. But oceans are cold. Below the thin surface layer, they're a fairly uniform 4 degrees Celsius. The wind-blown spray would be heated by contact with the hot air and carried up into the layers of air still blowing above, making room for more cold spray, which would be heated and rise, and so on. The subsequent turbulent mixing would likely trigger worldwide thunderstorms over the oceans. The wind would also have momentum, which would transfer into waves, which would sweep around the globe, west to east, and every west-facing shore would encounter the largest storm surge in world history. It would be like a combination of normal wind-driven waves and a tsunami.
Okay, yeah, that's... So whatever city isn't already destroyed somehow, I'm pretty sure everything would be. But even, I guess, some of the areas further towards the poles would still be affected by this water.
A turbulent wall of water would flow ashore, reaching in some places many miles inland. Eventually, a dense blanket of fog would settle over the cold ocean surfaces. Normally, this would cause global temperatures to plummet, and they would, at least on one side of the Earth. If the Earth stopped spinning completely, the normal cycles of day and night would end.
Okay, yeah, now we're getting into the long-term, tidally locked events.
The sun wouldn't completely stop moving across the sky, but it would slow down a lot. As the Earth's orbit carried us in a circle, we would see the sun rise and set exactly once a year. Well, not exactly once a year. The momentum of the atmospheric winds would get transferred back to the Earth, starting its spinning again very slowly, since the atmosphere is much lighter than the Earth.
Okay.
Relative to the distant stars, a single spin of the Earth would now take around 3,000 years to complete.
Wow. So I guess this is slightly different from being tidally locked, but I guess it's if the atmosphere somehow kept going again due to magic, the atmosphere could actually spin the Earth, which is crazy considering how light the atmosphere is relative to the Earth. But that's actually really impressive. I mean, yeah, 3,000 years is a long time, but the fact that there's still enough to cause it to spin, I didn't realize that. I figured it'd be tidally locked at this point.
So for all practical purposes, the once per orbit day that lasts a year would win out. Earth would experience 6 months of daylight and 6 months of night. On the day side, the surface would bake under the constant sunlight, while on the night side, the temperature would plummet. Although
boiling oceans and freezing oceans.
The length of the day would change, the length of the month would not. The moon hasn't stopped revolving around the Earth. In fact, the moon, our faithful companion, would act to partly undo what Andrew has done. Remember, this is all Andrew's fault. Before Andrew, the Earth's tidal bulge, created by the moon's gravity, slowed down our rotation while dragging the moon into a higher orbit. After Andrew stopped the Earth's rotation, the moon's gravity would tug on the Earth and very, very, very gradually speed us up again just a little while it slowed down. Until eventually, someone could again ask, what if the Earth suddenly stopped rotating?
So one other thing that he didn't mention as much in is this is going to cause all kinds of seismic activity with massive earthquakes, volcanic eruptions, just from that momentum from the Earth suddenly going to a halt. I mean, all of that energy's got to go somewhere when you pump the brakes like that. The Earth doesn't magically transform that energy into something else, so you're going to see it in a bunch of nasty seismic activity, including earthquakes, volcanoes, and there'd be regular tsunamis generated from those things. This might even be one of those scenarios that you'd get magnitudes over 10 just from pumping the brakes that hard. If you want to hear more about earthquakes, I'll pin a comment down to the video I reacted to about what would happen if a magnitude 15 earthquake hit Earth, and then you'd get the effects like the oceans moving to the poles. So you would even have a supercontinent going down the equator, which might even be one of the better spots to try to live on if you're trying to live right on the line between day and night to mitigate the effects of the freezing and boiling water temperatures on the rest of Earth. The biosphere would be reduced to a very tight zone, and it would be challenged by severe weather, so I don't think people are going to survive for much longer. the handful of survivors that are still there after a few months. Though I guess this scenario is slightly easier if you're keeping the atmosphere there, in the sense that the atmosphere is still rotating. All the oxygen didn't move to the poles, so the people could at least breathe in this case, but I don't think people are lasting much longer. What do you think?
Thank you, Moon.
What would a magnitude 15 earthquake look like? Well, nuclear engineers do account for seismic effects in reactor and facility design, but I'm going to tell you right now, nothing is standing up to a magnitude 15, if it were possible. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's check this out.
This is a question from Alex, who asks, what if a Richter magnitude 15 earthquake were to hit America at, let's say, New York City? What about a Richter 0 or 25?
In New York City, good luck finding a fault line to even get you to 10. 0 be tiny. 25, the Earth would not survive anything close to that. If you could somehow get it that high. So I guess 25 earthquake wouldn't really make a whole lot of sense.
Well, given that a magnitude 25 quake would destroy the sun if one happened there.
Destroy the sun. Yeah, there you go.
It would certainly destroy New York City.
That's awesome.
But we're getting ahead of ourselves. The Richter scale, which has technically been replaced by the moment magnitude scale, measures the strength of an earthquake. Since we usually hear about earthquakes with ratings somewhere between 3 and 9, a lot of people probably think of 10 as the top of the scale and 0 as the bottom. In fact, there is no top or bottom to the scale.
Nope, it's an exponential scale, no top, no bottom. And going negative does not mean you're going to have backwards earthquakes. It just means they're going to be really small.
But even if 10 isn't the top of the scale, it might as well be. A magnitude 9 earthquake already measurably alters the rotation of the Earth. The 2 magnitude 9 plus earthquakes this century both altered the length of the day by a tiny but measurable fraction of a second.
And there we go. The March 2011 one. The earthquake and tsunami that made everyone aware of what Fukushima even is. But yeah, that earthquake and tsunami was horrific. And what's crazy is over 18,000 people died from that earthquake and tsunami. And yet whenever it's brought up, it all seems to point to Fukushima, which had one direct death on site, not due to radiological release. And yeah, it did cause a massive evacuation, which likely the stress and panic for something like that is likely to take many years off of people's lives. But at least within my field, when remembering this, it's all about the nuclear accident. The tragedy seems to, of all the lives that were lost seems to be glossed over. I mean, even the Chernobyl accident didn't kill anywhere close to 18,000 people. Even if you go for the most conservative estimates and you're looking at the deaths that haven't happened yet due to long-term cancers, the most overly conservative estimates that continue into the future is 4,000 if you use the most conservative modeling. The most widely accepted ones for Chernobyl are in the 50 to 60 range. But yeah, 9 is big, and we mentioned 10 might as well be the top. I don't know if there's an actual fault line on Earth that could possibly give you a 10, because 10 is so much bigger than a 9.
In order to get to magnitude 10, you'd need a ruptured fault line 3,500 kilometers long.
Yeah.
And a magnitude 11 quake would require a fault that went halfway around the world. A magnitude 15 earthquake would be 1,000,000 times more powerful than that, and involve the release of enough energy to evaporate all the water on Earth.
So yeah, magnitude 15, that would make the asteroid that killed the dinosaurs look like a mosquito hitting your windshield. That asteroid impact, so just simply converting this magnitude into joules would give you between a 12 and a 13. So 15, nobody's surviving that one.
Though if that happened, we could rest easy knowing the earthquake couldn't cause any tsunamis. Going a few steps further, a magnitude 18 earthquake would release nearly 10 to the 32 joules of energy, which is roughly the gravitational binding energy of the Earth.
Yep, which is why I knew 25 was going to be way in excess, and apparently that's greater than the gravitational binding energy of the sun. And for those of you that are Star Wars fans, the Death Star's main weapon, which considering how quickly it blew apart Alderaan, and assuming Alderaan is similar enough to Earth, is on the order of 10 to the 38th joules, or about a 22. It's fun using orders of magnitude like this. To give you a sense of scale, the strongest nuclear bomb, the Tsar Bomb, was a mere 8.3. And Hiroshima and Nagasaki are about a 6. Now, I know this is earthquake, so this would be if you take that energy and channel it into a fault line, but it's interesting to play with these sort of numbers, I think.
To put it another way, the Death Star caused a magnitude 18 earthquake on Alderaan.
He brought up the Death Star before I did. I guess technically it would, because 18 would be the maximum in terms of if they measured it there. But if you measure it in terms of the Death Star's weapon output, I'm thinking it's closer to a 22, just considering it scattered the planet's mass far greater than escape velocity. But that one's a bit up for debate.
You could, in theory, talk about a more powerful earthquake on Earth, but in practice all it would mean is that the expanding cloud of space debris would be faster and hotter.
Kind of like the Death Star's main weapon.
The Sun, with its higher gravitational binding energy, could have up to a magnitude 24 quake. This is about the energy release you would get if you packed the entire volume of Jupiter with hydrogen bombs and detonated them all at once.
Wow, good luck finding enough materials to make all those bombs, getting enough uranium, plutonium. It might be cheaper to build the Death Star and use its magical power source. And good luck sinking them all at once to ensure one bomb going off just doesn't simply destroy some of the bombs. You would need a very precise sequencer, because with that many and how quick nuclear reactions are, you would need to account for the however many milliseconds of signal delay. And it would be great, and it would be more than an order of milliseconds if you want to be at a safe distance from this thing. Crazy.
The most powerful quakes in the known universe, which occur in super heavy neutron stars, are about this magnitude. A magnitude 25 quake would occur.
That makes sense. On the subject of neutron stars, one major advantage they have in terms of holding up compared to the sun is gravitational binding energy is inversely proportional to the radius. So you have say a 10 solar mass object, but it's got a much smaller radius, so it's going to take a much more powerful magnitude starquake to destroy something like that than even destroying the sun.
Explode the sun. Hold on, we're spending a lot of time thinking about things that are large and violent. What about the bottom end of the scale? Is there such a thing as a magnitude 0 earthquake?
So while we're on this subject, when designing a nuclear power plant to withstand earthquakes, you actually don't look at this scale. Instead, you look at the acceleration, which is typically given as some fraction of Earth's gravity. Because here you're talking about the Earth moving, so even, say, 0.1 g for a structure vibrating relative to Earth's gravity is a lot. And there's typically two parameters that get looked at. One is the operating basis earthquake, and that you mainly just look at your location and say, what is reasonable given the seismic history of the area? And say that's 0.05 G. And then there's your safe shutdown earthquake, which is typically much higher, say 0.1 G. And that is the earthquake that the plant, all of its safety systems, the acceleration that it can take, and everything will work properly. The reactor will safely shut itself down. All the safety systems, such as the emergency core cooling system, will inject safely into the core, say if there's a large reactor coolant leak, and be able to keep the core cooled, covered, and properly reactive. That's mainly what you look at when you design this criteria, and the safe shutdown earthquake acceleration needs to be much higher than the operating basis earthquake, which makes sense. You don't want to design something that isn't likely to stand up to what is known to occur in the area. One interesting thing is some of the more modern designs, like the AP1000 reactor, those facilities have safe shutdown earthquakes up to the 0.3 G range, which is pretty good considering the size of the structure and how much heavy equipment it has. Now, there's a lot of strict criteria that goes when designing a seismic facility and even just maintaining it. Like certain tool cabinets need to be anchored in in the right spot, and those are routinely inspected, and snubbers in the piping and joints of the facility are routinely inspected every outage, and there's a lot of them. I used to work closely with the principal engineer that walked down every snubber during every outage, every cycle, to basically ensure that the plant can withstand earthquakes, also hydraulic transients, water hammer, that sort of thing. And should the safe shutdown earthquake occur, then the emergency response procedures are basically to make sure everything shuts down properly. Everything should respond automatically, but there are additional options to manually shut down the reactor, manually initiate safety injection, either from the control room or locally if necessary. We do train on having to locally open the reactor trip breakers, but no, they are not in the reactor containment building like a lot of movies infamously portray. They are in the electrical auxiliary building, which is not even a radiological controlled area. Just have a plant operator open the breaker, hot stick the breaker if necessary, and all the control rods fall in a couple of seconds, and the reactor is safely shut down. No radiological PPE required. Though if they're hot sticking a breaker, arc flash PPE is required, which is actually heavier than radiological PPE usually.
Yes, in fact, the scale goes all the way down past 0.
Yep.
Let's take a look at some low-magnitude earthquakes with a description of what they would be like if they hit your house. A magnitude 1 quake releases the same energy as dropping a partially loaded cement truck from 10 meters onto the street in front of your house.
That's great. Yeah, it would create a bit of a shockwave, but things below a 3 you typically don't feel, or you might not even notice that much. And something as transient as that, I mean, and here we're talking the entire, like basically the maximum amplitude. So if this were to happen, you might not even notice it very much. It would just be a thud, not a rumble or a temblor or anything like that. One other misconception about the Richter scale is a lot of people think each increase is a factor of 10, but that's not the case. It's actually worse. So you go by a magnitude of 2, so you go from 1 to 3, that's a factor of 1,000, not a factor of 100. So going up from 1 to 2 is an increase by about 30-something in terms of energy released from the earthquake.
A magnitude 0 earthquake is equivalent to the Dallas Cowboys American football team running at full tilt into the side of your neighbor's garage. A magnitude -1 quake is like a single American football player running into a tree in your yard.
Silliness. So in nuclear engineering, we actually use a scale similar to that for doing a reactor startup. It measures it in startup rate, and the unit is decades per minute. 1 decade per minute is power level going up by a factor of 10 in a minute. And the meter does look something like this, though the units are a lot tighter. So at a commercial nuclear power plant, a good startup rate going into the point of adding heat, which is when you get a natural feedback mechanism from the higher temperature to slow the fission reaction down in a pressurized water reactor. And going into that, you're usually going at about 0.3, 0.2 decades per minute. Or reactor power going up by a factor of 10 in 3 to 5 minutes. It's a very slow, methodical process. Now, a submarine reactor, during a startup, the limit is 5 decades per minute, or power going up by a factor of 10,000 in a minute. And a fast recovery startup, the limit is 9 decades per minute, which is a factor of 1 billion in a minute. So going from microwatts to megawatts pretty quickly. The limit in the commercial nuclear power plant is 1 decade per minute. I've never seen anyone go anywhere near that fast. I don't even think you can. There's just not enough acceleration, for lack of a better word, in the reactor core. So nuclear submarines are like sports cars, and commercial nuclear power plants are like freight trains in terms of acceleration. There is another way of determining how fast the reactors start up, and that's by using the reactor period. That's not a rate, that's a unit of time for reactor power to increase by a factor of E. E being 2.71 and some change. I've never used that in commercial nuclear. I've seen that come up at research reactors. Clearly a bunch of nerds that think in terms of E rather than factors of 10. At least to me, that's less intuitive to me anyway. I don't know. Hey, if you think better in terms of E, more power to you.
Cat falling off a dresser would have a magnitude of -2.
What? The cat didn't land on its feet?
A cat knocking your cell phone off your nightstand would have a magnitude -3.
Yeah, you deserve that.
Magnitude -4 is like a penny falling off of a dog. Magnitude -5.
I love this scale. Usually you do the crazy extreme big examples first, but here we're doing the teeny tiny gentle ones. I like it.
5 is a key press on an IBM Model M mechanical keyboard. -6 is a key press on a lightweight keyboard.
I don't know. I'm not sure I believe that one. I've known some pretty aggressive typers. Are you sure they're not up to a 0 or even a 1? I love it.
-7 is a single feather fluttering to the ground. A fine grain of sand falling onto the pile at the bottom of a tiny hourglass would be a magnitude -8 quake. And let's jump all the way down to magnitude -15, a drifting mote of dust coming to rest gently on a table.
Wow, that's already down to, well, dust is so light. Wow, that's awesome.
Sometimes it's nice not to destroy the world for a change.
The one thing I will say is one individual fission event of a uranium-235 nucleus, which is about 200 million electron volts, figures out to about -11.5, which is actually a lot, considering that this is just one teeny tiny nuclear reaction as part of a nuclear power plant. After all, a nuclear power plant is about a 3.2 every second, constantly, for 18 to 24 months. Because remember, the energy yield from these earthquakes are typically momentary, seconds to minutes. But the thing nuclear power has is sustainability on its side. I really like this video. Thanks so much for the recommendation. I love playing with bizarre units of measure, such as the Richter scale, and turning them into other things. What if all the lightning on Earth struck the same place at once? All the lightning. So, like all the strikes over the course of a year? Well, bolt of lightning's 1 billion joules, and that's conservative. And 1 billion lightning strikes a year. If you convert that to megatons, that's gonna get you well over 200. And the most powerful nuclear weapon is 50, so we're talking quite a bit of energy. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's check this out.
This question comes from Trevor, who asks, if all the lightning that occurs worldwide on any given day all struck in the same place at once, what would happen to that place?
Okay, so we're scaling it down to a day. So dividing that number I just said by 365, you're going to get 650 or so kilotons. So not nearly as crazy, but we're still talking well above the average nuclear weapon in terms of yield. Now, big asterisk there, though, because lightning isn't very predictable. So when I said 1 billion joules or a gigajoule, that's a rough and conservative average. You can have some really big lightning, upwards of 10 billion joules, or you can have some really tiny lightning, of less than 100 million joules. So it depends. And keep in mind, sources do vary a bit. I've seen some that claim the average of 7 gigajoules, 3 gigajoules, 5 gigajoules. I'm just going to assume 1, mainly because that's an easier number to work with, but lightning can get pretty strong, a lot stronger than that.
They say lightning never strikes in the same place twice.
I've heard that saying. I do not know where that comes from. If that was the case, any sort of device that protects you from lightning, such as a lightning rod, a grounding grid, or a surge arrestor, could be single use and you'd be fine. I'm pretty sure there are places of the world where lightning strikes the same spot pretty regularly. I have no idea where this came from.
They are wrong, and it's a little surprising that this saying has survived.
Yeah.
You'd think people who believed it would have been gradually filtered out. People often wonder whether we could harvest electrical power.
I guess lightning doesn't strike enough in the same spot to take all those people out of the gene pool.
Power from lightning. On the face of it, it makes sense. After all, lightning is electricity, and lightning strikes seem pretty powerful. The problem is, a lightning strike is over so fast that the total amount of energy delivered isn't that extreme, and in any case, it's very hard to get lightning to strike where you want it.
Yes, so lightning lasts on the order of microseconds. So you can get some pretty extreme power levels, but it's not sustainable. Can't imagine trying to use it as a power source. Silliness. So neglecting that Doc Brown would have been electrocuted, and I highly doubt those cables were rated for 300 million volts and 30,000 amps. You could get 1.21 gigawatts, as they say, in Back to the Future, keeping in mind it's actually pronounced gigawatt, but it's over such a short period of time. Using it as that way in a power plant, no. Though keep in mind that nuclear power plants, in the reactor, the plant I worked at was close to 4 gigawatts, and that's constantly over the course of 18 to 24 months, which still translated to about 1.4 gigawatts or 1,400 megawatts going onto the grid from the main turbine. So it's a bit of a weird thing when you can talk about how much power something produces, but if it's not sustained, it doesn't really mean anything. Like, you can have pulse laser tattoo removers that are technically in the megawatt range, but it's just emitting that laser pulse over such a short period of time. Not exactly an impressive showing for something that's in the megawatt range, but you can get to megawatts by dividing by a really small number.
A typical lightning strike delivers enough energy to power a residential house for about 2 days.
Okay, and I can even see his notes saying it uses far more energy, but a lot of it does go away by the time it reaches the ground. That's also true. So 2 days. Okay, so the number he's using is only about 200 to 300 million joules. Because we're talking 30 to 40 kilowatt hours per day. The conversion for kilowatt hours to joules is 3.6 million.
That means that even the Empire State Building, which is struck by lightning about 100 times a year, wouldn't be able to keep a house running on lightning power alone.
Yeah, lightning isn't very energy dense. It's impressive looking, but it doesn't last very long. Even solar power has such a major leg up on it because the sun is at least constant, or wind power for that matter. Because while it's not as impressive as lightning, lightning certainly looks a lot cooler. The sun shines a lot longer and the wind blows a lot longer. So even more mundane, ordinary things like that could give you a lot more energy. And of course, nuclear power produces so much more energy than wind and solar, and from a much smaller power source.
Even in regions of the world with a lot of lightning, such as Florida and the eastern Congo rainforest, the power delivered to the ground—
I actually didn't realize Florida had a lot more lightning than average. That's good to know.
—by sunlight outweighs the power delivered by lightning by a factor of 1,000,000.
There you go. I like how we kind of agree on a lot of things, because yeah, you're going to get a lot more from your solar panels, lest your solar substation get struck by lightning, but hopefully they have a lot of lightning protection systems that you would in any substation or power generation site like a nuclear power plant. In case you're wondering how a nuclear power plant protects itself from lightning, well, first off, the buildings are heavily reinforced. The reactor containment building, for one, as well as the control room building, which is not in the containment building. It's actually in an auxiliary building to the side known as the electrical auxiliary building, made out of reinforced concrete and steel. So that'll protect you from lightning, among other natural phenomena, such as high wind, flooding, earthquakes, a lot of things. They also do have lightning rods installed at the top of these structures, which are connected in conductive pathways that essentially channel all of that energy down to the ground. And there are grounding grids installed around the plant, just conductive materials buried down in the ground to ensure it's dispersed safely into the earth. And just about every structure is grounded, not only from lightning, but just any sort of power surge. I mean, we're dealing with high voltage electricity. So surge arresters and suppressors protect against any kind of voltage spike, including the spikes of voltage you get from lightning. And there's protective relays in just about every electrical component for overcurrent, overvoltage, and undercurrent and undervoltage, for that matter, among just about every type of lockout device there is. Nuclear power plants invest a lot in their electrical protection. And if you do lose something, the electrical plant is set up that you don't lose large chunks of it at once. But even if you did, even if you lost the entire grid, there are backup diesel generators that can provide emergency power and uninterruptible power supplies. And keep in mind, these diesels, at least the safety-related ones, are actually located inside of structures. The diesel generator building is also a reinforced concrete structure, so the diesel itself isn't going to get struck by lightning. Not to mention, we have weather towers, meteorological towers that can be used to predict where the severe weather and the lightning strikes are coming in, so the plant operators can initiate protective actions. And the main thing that is initiated during a lightning proximity breach is about protecting the plant operators and maintenance technicians, having everybody on outside elevated structures and confined spaces evacuate those areas until they're given a lightning all clear. Plant and its safety systems are so robust compared to other natural phenomena such as earthquakes. Lightning isn't going to do a lot to the plant. To put it this way, all of our lightning procedures are all about protecting people in vulnerable areas, not so much about protecting the plant. It's more of, if the lightning gets bad enough that you lose the grid, you initiate your response to loss of off-site power procedures where you ensure the reactor is safely shut down and everything is being carried by the emergency diesel generators.
This makes sense because ultimately lightning is powered by sunlight. Generating power from lightning is kind of like building a wind turbine powered by tornadoes.
Lightning powered by sunlight? I suppose indirectly. I mean, you're talking about the sun influences the weather patterns on Earth. Solar heating heats the Earth's surface, forms convection currents, updrafts, thunderstorms, and then, yeah. Here you have it. Guess I never thought of it that way.
Impractical.
That is pretty silly, yeah, so to only have a power source that relies on the extreme version of something rather than just the normal, sustainable, boring version of something. But yeah, in this example, solar and wind turbines are the boring but practical solution, rather than the tornado exclusive turbine that would require wind speeds of over 70 meters per second to even be relevant. Whereas wind turbines typically stop functioning when cutout speeds for wind turbines where they stop producing electricity are well below 40 meters per second. Also, tornado food. What is that? Mobile homes?
Although that would also be very cool. In Trevor's scenario, all the lightning hits the world in one place. That would make power generation a lot more attractive. By happen in the same place, let's assume that the lightning bolts all come down in parallel right up against each other.
Wow.
The main channel of a lightning bolt, the part that's actually carrying current, is about 1 centimeter or 2 in diameter. Our bundle contains about 1 million separate bolts, which means it'll be about 6 meters in diameter.
So I guess he's being a little conservative, since it was 1 billion a year, so we're cutting down to a day. So he's dividing by 1,000 rather than 365. Okay.
Hitting a region of the ground the size of the center circle of a basketball court.
It's gonna be like just some crazy plasma weapon.
Every science writer always compares everything to the atomic bomb dropped on Hiroshima.
Which I don't even know why. It's crazy because it's coming up on 80 years and modern nuclear weapons are a little different, but I guess that's left such an impact that people like to use that as a method of comparison.
So we may as well get that out of the way. The lightning bolt would deliver about 2 atomic bombs worth of energy to the air and ground.
Okay, so 2 atomic... That's small, because that's only 32 kilotons. Then again, he's actually being conservative because he's only saying 1 million bolts, and he also used the 200 to 300 million joules per bolt. So I can see how he's getting a smaller number than the 600-ish kilotons going with the average numbers. Though he's talking about hitting the ground and a lot of the and he's talking about the energy being dissipated. So really, at the top of that is where you're going to get your 600 kilotons of lightning plasma energy. Keep in mind, he's talking. This is a very conservative estimate that he is saying, and There are bolts of lightning that are a lot stronger than this, so if you want to get the full range, this is close to the low limit, and the upper limit will, even if you scale it just to a day, can probably get you into the megaton range. So there's quite a wide range here because lightning is so weird and varied.
From a more practical standpoint, this is enough energy to power a game console and TV for several million years.
Oh, that's the Nintendo 64. I wonder if he's playing Ocarina of Time. In that case, the real question is, how many times would you have to play the Song of Storms to generate this much lightning in one location? I mean, hey, in that game, the Song of Storms was formed by a time paradox, so creating massive directed energy plasma weaponry should be comparatively easy, right?
Or to put it another way, it could support the US's electricity consumption for 5 minutes.
See, that's the other thing. Uses a lot of energy, but all the lightning in the world for a day, translating to 5 minutes for just one country. Not a very efficient way to generate electricity. Let's stick with nuclear power plants as part of a complete, well-balanced energy portfolio. I'm biased, of course. In case you're wondering how much energy that is, the US uses about 1.3 million megawatts, or about 1,000 nuclear power plants worth, if you're just sticking with about 1.3 million megawatts, or about 1,000 nuclear power plants, if you were to have the entire US run on nuclear power. That's about how many it would take. As of now, the US has just under 100 nuclear power plants, or nuclear reactors. Some power plants have more than one reactor.
The bolt itself would only be as narrow as the center circle of a basketball court, but it would leave a crater the size of the entire court. Inside the channel, the air...
Keep in mind, these are all lowball estimates. Yeah, it'll do a lot more than just a basketball court.
Would turn to high-energy plasma. The light and heat from the bolt would spontaneously ignite surfaces for miles around. The shockwave would flatten trees and demolish buildings. All in all, the Hiroshima comparison isn't far off.
Yep, that's a lot of plasma, air ionization, and if it's the bigger one of this, yeah, several kilometers would be affected. There would also be an EMP. Now, not each individual bolt will cause an EMP, but enough of them from thunderstorms could cause an EMP shock, especially if it's concentrated like this. So it could disrupt electronics, power grids, especially since it's a bolt, it's going all the way up into the atmosphere. It's going to have a more widespread effect than this concentrated hit like this. Oh, and lightning does generate radiation, too. Now, at ground level, even concentrated, we're not talking about the levels from an atomic bomb. It's going to be a pretty wide spectrum. Obviously, the visible light, the visible radiation that you can see, radio waves, UVs, but even some high-energy gammas and X-rays. Though, keep in mind, everything is really quick flashes, just like the nature of the visible part of the lightning strike. It's a quick flash, and you'll see it in the upper clouds of a thunderstorm.
You might hope you could collect the energy of the bolt using a lightning rod. The mechanism by which lightning rods work is actually disputed. The traditional idea is that they provide a channel to divert current directly to the ground, while some people claim
that's what I was taught, okay?
That they actually ward off lightning strikes by steadily transferring charge from the ground to the air.
Huh. I haven't heard the one of it spitting out positive charges like that. But, you place it on the highest point, it concentrates it in, and it safely conducts it down the building all the way down to the ground, and the energy is dispersed into the earth. But hey, if there's another theory out there, I know a lot of stuff about lightning we just don't know as much about, hence probably the high energy bands that are quite unpredictable. So I fully welcome being wrong about this.
Lowering the cloud-to-ground voltage difference and reducing the probability of a strike. Either way, a lightning rod wouldn't keep you safe from Trevor's lightning. A copper cable a meter in diameter could, in theory, conduct the brief surge of current from the bolt.
Oh, that's cool.
Without melting, but unfortunately, whatever's at the other end of this cable probably wouldn't conduct electricity nearly as well. And
it's just too much energy in one concentrated area is the thing. And yeah, good luck having 1 meter long cables going like super, super far down.
An explosion would disintegrate everything nearby all the same. Collecting all the world's lightning into one place is obviously impractical. But what about gathering all the lightning from just one area? No place on Earth has constant lightning, but there is an area in Venezuela which comes close. Near the southwestern edge of Lake Maracaibo, there's a strange phenomenon: perpetual nighttime thunderstorms.
I've heard of these. I wasn't sure where they were, but yeah, that's one quick way to disprove the whole lightning's never striking in the same place twice. It's like, well, just go over here and take a look.
There are two spots, one over the lake and one over the land to the west, where thunderstorms form almost every night. These storms can generate a flash of lightning every 2 seconds, making Lake Maracaibo the lightning capital of the world. If you somehow manage to channel all the bolts from a single night of Catatumbo thunderstorms down through a single lightning rod and used it to charge a massive capacitor, it would store up enough power to run a game console and TV for roughly a century.
There you go. Maybe someone did the thing where they just played the Song of Storms over there and plugged it in so they could continue to play Ocarina of Time.
If this happened, we'd probably need to revise the old saying to something like, lightning always strikes in the same place. That place is in Venezuela. You shouldn't stand there.
That's funny. This was a really cool one. I always love these crazy scenarios and how you can use some elements of real physics to talk about it, as far as how you'd get the lightning there and move like all the world's clouds into one spot. Not sure, but I like that there's a good balance between science and suspension of disbelief in these scenarios. I can see why it's so popular and entertaining. If all humans died, when would the last light go out? Now, nuclear power plants can keep lights on for a very long time, but they do require reactor operators and plant operators. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's check this out.
This question comes from Alan, who asks, if every human somehow simply disappeared from the face of the Earth, how long would it be before the last artificial light source would go out?
My initial thought is lights powered by RTGs would last the longest. Now, an RTG, or radioisotope thermoelectric generator, converts heat from the natural radioactive decay of isotopes into electricity, usually uses something like plutonium-238, releases heat. The heat is absorbed by thermocouples, which is made up of two different types of conductors, and the temperature difference between the hot radioactive material and the cooler exterior environment creates a voltage across the thermocouples, and it generates an electric current. And this is typically used for remote instruments that you don't want to send somebody to go out and replace, or space probes. And this can last for decades to centuries, so can't really think off the top of my head of anything that lasts longer than that. Any light source powered from this.
We'll start with the obvious. Most lights wouldn't last long because the major power grids would go down relatively quickly. Without people, there would be less demand for power, but our fridges and air conditioners and lava lamps would still be running.
Yeah, if everyone disappeared instantly, no one is actually turning off any of these lights. So whatever automatic set point is gonna essentially keep running. And if any weather effect comes in, takes out the grid, no one's going to pick it up. Drones aren't that sophisticated yet that they can do full repair process from critical de-energization up to critical switching to get power back. We're not there yet.
Fossil fuel plants, which supply the vast majority of the world's electricity, require a steady supply of fuel, and their supply chains do involve people doing things. As coal and oil plants started shutting down in the first few hours, other power sources would get hit with that extra load.
Coal has to be continuously fed just because it uses tons and tons of the stuff to be fed in by train. Though, I actually think the first lights to go out would be those little motion sensor lights that sometimes annoyingly go out while you're still in the room. I've been in a few conference calls in the office where I have to jump up and down just to get the lights to come back on. So those would probably be the first ones to go. But once you get to this point, you're going to have to, well, normally grid operators would prioritize this, but one challenge you run into with suddenly dropping a bunch of large generators could be the inability to maintain grid frequency.
This kind of situation is difficult to handle even with human guidance, and the result would be a rapid series of cascading failures leading to a blackout of all the major power grids.
Yes, that could definitely happen. Even generators from nuclear power plants would trip offline just due to being unable to maintain grid frequency. So if, say a drone or whatever was monitoring the control room in a nuclear power plant, that's not what actually happens, but the generator is going to trip on under frequency because most of the grid went down. Just going to automatically happen to protect the generator, so the nuclear power plant's going to be offline. And what's going to happen to the reactor when that happens, it's going to automatically shut down. Because when you're at 100% power, the reactor trips following a turbine trip. Now, when I say reactor trip, I'm talking about the reactor trip breakers opening and all of the control rods falling in, shutting down the reactor in a couple of seconds. So for the vast majority of nuclear power plants, despite it being nuclear power and having one of the best fuel sources and actually far than enough fuel to keep going for 18 to 24 months even after this happens, they're going to be offline when the grid goes offline due to automatic protective relays. And for the ones that are less than 50% power, they're still going to trip offline, but just not immediately. It's going to take a few seconds to minutes because another reactor trip relay will activate, but this time due to the rapid cool down that would occur from losing the generator. The reason why it doesn't automatically trip when you're less than 50% power is because there are operational procedures that reactor operators can execute to keep the reactor online safely after the turbine has tripped. But there's no people in this scenario, so the reactor will still trip automatically. Just being below 50% will buy you a few seconds to minutes. So this is one scenario that even nuclear plants are not going to last very long as far as supplying the grid. Now, the reactor is still going to be safe for a while.
Nuclear reactors, of course, don't require a steady supply of fuel. One reactor operator I talked to said that if their core settled into low power mode, it could continue running almost indefinitely.
Depends. So that depends on reactor design, and it depends how low. If you're low, like you're not even on the grid yet, then yes, the reactor is still operating, but it's not supplying the grid. Now, it could theoretically keep running as far as the reactor operating, but it's not supplying the grid. One other thing that could occur, now this depends on the reactor design. If it's, say, a pressurized water reactor, just the act of losing off-site power would automatically trip the reactor when you're above 20 to 40% power. Again, this is more design specific. Just because you lost your reactor coolant pumps, and there is another protective relay that will trip the reactor because you don't have that forced circulation. Yes, nuclear power plants could theoretically run on natural circulation, but certain designs, they just won't let you. A lot of submarine reactors, for instance, can work on natural circulation. And when I say natural circulation, I'm just talking about temperature differences between the hot and cold part of the reactor coolant system rather than a pump forcing a circulation. Operating on natural circulation is just super slow for things like controlling temperature. Because forced circulation, reactor coolant pumps flow is on the order of hundreds of thousands of gallons per minute. So water is circulated through the loops in a matter of seconds. So any adjustment you make, you'll see pretty much right away. But on natural circulation, said transit time goes from 10 seconds to like 15 minutes. So it's a much slower method of control. Thus, the automatic protection system that you don't want reactor above a certain power level while you're on natural circulation. In fact, procedurally, at the plant that I worked at least, you don't want the reactor running at all. The reactor is required to be shut down. But again, in this scenario, there's no people, so no procedures unless they're followed automatically. But strictly based on relays, certain designs, the reactor would shut down right away as soon as you lose the grid.
A cube of uranium contains about 6 million times as much stored energy as a similar-sized cube of coal.
I love this chart right here, by the way. And yep, that's absolutely true. I like that fat has higher energy density than coal. That's pretty good.
Unfortunately, although there's enough fuel, most nuclear reactors wouldn't keep running for long. As soon as something went wrong, the core would go into automatic shutdown. Every part of a reactor control system is designed so that a failure causes it to rapidly shut down. This would happen quickly. Many things can trigger a shutdown, but the most likely culprit would be the failure of the power grid.
Yep, that's just it. And that will shut down, like you said, both the turbine first, and depending on power level, the reactor, or depending on design, the reactor right away. And the time difference between turbine and reactor, we're talking on the order of milliseconds, because it's just however long it takes for one relay to trigger another.
However, plenty of light comes from sources not tied to the major power grids.
That's true.
Let's take a look at a few of those and when each one might turn off. Many remote communities, like those on far-flung islands, get their power from diesel generators. These can run until their tanks run out of fuel, which in most cases could be anywhere from days to months.
One thing I will say is at the nuclear power plant, even after the reactor is shut down, so all the safety systems, for instance, would still be protecting the nuclear power plant. And there would still be lights on there, and they would all be powered by diesels. And diesels, now they're designed to last at full load, like all your emergency systems flowing at max rate for about a week. In this scenario, they're going to last significantly longer than that because it's mainly just going to be about what it takes to manage the decay heat, because no accident occurred. They're designed to deal with, you have a major nuclear accident and you've lost power at the same time. But here, we're just losing power for a while. And the challenge, so I'll say the challenge that occurred with Fukushima is, so reactor cores still generate decay heat. Spent fuel pools still generate decay heat. So cooling systems are going to need to operate continuously to maintain that. Now they're being provided by backup diesels. So in this scenario, there's no earthquake or tsunami. So we're assuming that none of the safety systems got damaged as a result of all of the humans going poof. So don't know about 6 months. 6 months could be like this guy just using a light bulb or something. Like the light bulb will probably be burnt out before the diesel runs out of fuel, depending on what type of light bulb it is, unless it's an LED or something. But probably a month at most, though, just to run those diesels at low load. But we're talking at most. It could be 2 weeks, 3 weeks. But as soon as those diesels die, there's still batteries. But batteries, even at low load, a day at the absolute most. Maybe just a few hours. There's actually procedures that we have to load shed batteries if you're dealing with a total loss of all AC power, so that all your diesels fail somehow, and you're dealing with a station blackout, then there are procedures that you load shed those batteries for loads that are, say, just for the main turbine, that aren't really important to nuclear safety, but it is protecting the asset. So you shed those, so you basically save your batteries for the stuff that needs it the most. And a lot of times, and in most designs, including the one that I worked at, they kept it separate. The ones for vital turbine loads versus, say, the vital nuclear safety related loads. But that'll just get you a few hours to a day at most on top of the diesel length. And now you're not going to have a meltdown immediately when that happens. That's just when things are going to start to heat up.
Off-grid generating stations that don't need a human-provided fuel supply would be in better shape. Geothermal plants can run for a fair bit of time without human intervention. According to the maintenance schedule for the Svartsengi Island geothermal plant in Iceland, every 6 months the operators must change the gearbox oil and re-grease all electric motors and couplings.
Now, does this geothermal plant connect to the grid, though? Because it would still be vulnerable, just how a generator works, it would still be vulnerable to an under-frequency event. But if it's isolated and it's on an island, as you say, meaning not connected to the grid, it doesn't really have to worry about that under-frequency issue. This particular plant, I don't know, but that's the main hazard with anything that connects to the grid.
Without humans to perform these sorts of maintenance procedures, some plants might run for a few years, but they'd all succumb to corrosion eventually.
That's true. I mean, yeah, 3 years, that affects nuclear plants too. Nuclear plants are actually, they need additional maintenance for corrosion due to neutron embrittlement. When neutrons pass through metals, pipes, things, over a very long period of time, they could just make the structure more brittle, meaning throughout the duty cycle of a nuclear plant, you'll just have to do more maintenance activities and probably replace those pipes sooner. Though, then again, nuclear power plants also have pipes that are more resistant to that. They're just more expensive.
Lights relying on wind power would last a bit longer. Wind turbines are designed so that they don't need constant maintenance for the simple reason that there are a lot of them and they're a pain to climb. The Gedser wind turbine in Denmark was installed in the late 1950s, and it
The thing about wind turbines is they're super vulnerable to the weather. They're notorious for getting struck by lightning and catching fire, and they're a lot more resistant to a lot more susceptible to natural disasters compared to, say, nuclear power plants, which go through a much more robust seismic engineering qualification process.
Generated power for 11 years without maintenance. Modern turbines are typically rated to run for 3 years without servicing, and there are no doubt some which would run for decades. And one of them...
The 20 years ones are kind of few and far between. This is one of the things about wind power is they're not exactly recycled very well either when, say, that three-year turbine. I mean, yeah, you can refurbish and repower them, but it's not exactly the... that's one of the big criticisms behind wind power is it really that green if you have to do that? Now, they are getting better, just like any piece of technology, and there are good examples, but it's definitely been an issue. Plus, there is some level of manual operation required. You can pivot them, you can kind of change the pitch slightly to just have them be more effective, to position them where the wind's actually blowing, so you can maximize their effectiveness at generating electricity. But that should still probably keep a light bulb on if it's in that same general position. But you're also, again, if the wind's not blowing, then that'll make your light go out. So the wind is too dependent on external factors. 20 years, maybe. So 20 years, I'm going to put an asterisk by that one.
Probably have at least a status LED in it somewhere. Eventually, most of the wind turbines would be stopped by the same thing that would destroy the geothermal plants. Their gearboxes would seize up. Generators...
Anything involving rotating equipment has the potential for equipment failures like that. So any turbine, whether it's a wind turbine, a nuclear power plant turbine, coal power plant, it can have an unpredicted failure like that. Now, back to the nuclear plant. So after it loses all of its cooling functions, decay heat does decrease over time. So you can see how power goes way, way down after the reactor is shut down. However, 1 megawatt is the equivalent of basically 1,000 household microwaves on high, so that's still a lot of energy. So it is going to heat up the water. As far as when that happens, it depends on a number of factors, like how recent was the fuel that's in, say, your reactor used, like how far along in the fuel cycle they are, as far as how much decay heat is there. Because it's from the fission products, not the uranium itself. So if you have a bunch of fuel that's burned up, it's actually going to generate more heat from all of the decay products. So the good news is the backup systems will cool down the reactor when it's needed the most, but it's still going to heat up. And water would probably start to evaporate within 2 to 3 months, again, depending on where your initial condition was. And this is bad. Because this will also happen in your spent fuel pools, that as temperature rises, the zircaloy cladding starts to react quickly with the water. That reaction will accelerate as temperature goes up. So it's going to look much like the opposite of this graph when that happens. And that could potentially heat up and catch fire, causing the release of radioactive material. Now, the containment building's still going to work at this point, so we're not talking about radioactive material getting out and getting exposed to, well, I was going to say the public, but nobody's here, getting exposed to animals in the nature preserve, because nuclear power plants are often built around nature preserves, so I guess at this point we're talking about protecting animals. Now, the spent fuel buildings would be more of a hazard, because they don't have the same pressure release that's designed to resist explosions that the reactor containment building is. And the reason for that is they're not designed to hold that much fuel for like decades, centuries, whatever time frame we're getting to, because they're eventually going to go into dry cask storage. Now, the ones in dry cask storage, they're going to be fine for centuries even. But the fuel handling building, that is eventually going to fall apart due to these internal fires and explosions that would occur. And that's going to be where the radiological release is going to happen first. So, longest, I'm thinking spent fuel pool, fuel handling building, radioactive release. Now, normally it does have protective HVAC systems to keep contaminants inside the building, but, well, the building's destroyed at this point. So that probably within a year. The reactor containment building within decades, and dry cask storage, well, I know I should never say never, but there you're dealing with a much longer timeline, many, many decades, possibly centuries, maybe even a few millennia. Those we don't even really know that much because you're dealing with such a long time scale. There's so many crazy things that can happen. When you're dealing with timelines on that scale, you could say, like, odds are you're going to have a super crazy earthquake or an asteroid impact or something like that is bound to happen eventually. Though I will say a lot of the medium range radioisotopes, such as cesium-137 with a half-life of, say, 30 years, those will have surely decayed away by the time you get to dry cask storage issues. They're definitely going to be a hazard when the fuel handling building fails, but those and probably the worst fission products are going to go away. Now, you're still going to have some radioactivity because some, like uranium-235, has a half-life on the order of hundreds of millions of years, but it's not nearly as radioactive as, say, cesium-137 or strontium-90. So, yeah, even after, you're still going to have some levels of radioactivity, but it's not going to be, say, like the Chernobyl or Fukushima or anything like that, because those happened much shorter timescales.
To convert falling water into electricity will also keep working. An operator at the Hoover Dam once said that if everyone walked out, the facility would continue to run on autopilot for several years. So if the power grid is down, all that electricity would have nowhere to go.
And that's really it. So yes, even say a passive thing about a completely passive system that you're just relying on a gravity difference. Yeah, that part's going to run. So the mechanical bit's going to run is going to run, but again, it's not going to generate anything because it's the same generator problems with grid underfrequency.
In the end, the dam would probably succumb to clogged intakes or the same kind of mechanical failure that hit the wind turbines and geothermal plants. Battery-powered lights wouldn't fare much better and would all be off within a few dozen years. Even without anything using their power, batteries eventually self-discharge.
Yeah, and if the battery was on your flashlight, it's just going to last a few hours anyway.
Some types last longer than others, but even batteries advertised as having long shelf lives typically only hold their charge for a decade or two.
Yeah.
Solar power is probably the most promising candidate. There are many off-grid solar-powered buildings, weather stations, and other remote infrastructure around the world.
Provided you don't have extended cloudy periods and the solar panels do not get hit with hail or any other sort of natural disasters. So what's interesting is these renewables, they will actually last longer than a nuclear power plant, mainly as far as generation, just because they're not necessarily playing with the big grid, but they're so much more vulnerable to weather-related things that's kind of the big question mark here behind all these. But yeah, I do agree they do have the potential to last a while, just provided nothing happens to them.
The call boxes, often found along the side of the road in remote locations, are frequently solar powered. They usually have lights on them, which provide illumination every night.
I was actually about to say those school zone speed limit signs. They have solar panels like that. But those only come on intermittently anyway, so those could potentially last a pretty long time, whereas this is more of a continuous bulb.
Like wind turbines, they're hard to service, and so they're built to last for a long time. Solar panels will generally last as long as the electronics connected to them, and as long as the panels are kept free of dust and debris. The wires and circuits will eventually succumb to corrosion, but solar panels in a dry place with well-built electronics could easily continue providing power for a century if they're kept.
This one it would have to be a pretty lucky century, but I guess theoretically.
Free of dust by occasional breezes or rain on the exposed panels. If we follow a strict definition of lighting, solar-powered lights in remote locations could conceivably be the last surviving human light source. But there's another contender, and it's a weird one. Spent nuclear fuel. Contrary to popular portrayals, radioactivity isn't usually visible, which is part of why we need warning signs around areas with
Is he referring to Cherenkov radiation?
Radioactive materials or waste. Sure, watch dials used to be coated in small amounts of radium to help them glow in the dark, but the glow didn't come from the radioactivity itself. It came from the phosphorescent paint on top of the radium, which glows when it's irradiated. Once the phosphorescent paint breaks down, the watch dials are still radioactive but no longer glow.
Oh, and that was an infamous example of the radium girls that, they licked the paint brushes to get everything straightened out, but ended up getting horrific tongue and throat cancers from the increased dose. Yeah, that whole process violated several hundred radiological safety procedures that didn't exist back then, unfortunately. And the sad part is, the people that told these women to do this, they knew the hazards, at least enough of it to know that's a bad idea.
Watch dials, however, are not our only radioactive light source. When radioactive particles travel through materials like water or glass, they emit light through a sort of optical sonic boom. This light is called Cherenkov radiation, and it's seen in the distinctive blue glow of nuclear reactor cores.
Yeah, basically what happens when you break the light barrier. Particles traveling faster than the speed of light in water. You can't go faster than C, but you can go faster than light that's going slower than C.
Some of our radioactive waste products, such as cesium-137, are melted and mixed with glass, which cools into a solid block before being wrapped in more shielding for transport and storage. And in the dark, these glass blocks glow blue. Cesium-137 has a half-life of 30 years, which means that 2 centuries later, the blocks will still be glowing with 1% of their original radioactivity.
That's true, and while cesium is natural, the way this cesium got there was not natural, it was from artificial means. The challenge to this, though, is I don't know of any spent fuel pool that is going to maintain cooling for 200 years without human intervention. Because they're not going to glow in dry cask. Because it's dry, there's no water to give it that glow. So, while cesium could theoretically last 200 years in water this way, you would have to take some and chuck it into the ocean, because the spent fuel pool after 200 years is going to be destroyed. But I guess this scenario could work. You have a submarine crash, and then somehow the reactor guts spill out into the ocean. Then, yeah, you could potentially have this. Though RTGs, lights generated from RTGs, could potentially last on the order of centuries. But I like this example, because this isn't the one that I initially thought of, despite it being a nuclear thing.
Since the color of the light depends only on the particle decay energy and not the amount of radiation, it will fade in brightness over time, but keep that same blue color. And thus, we arrive at our answer. Centuries from now, deep in concrete vaults, the light from our most toxic waste will still be shining.
Interesting he didn't mention RTGs, though. And these would be like teeny tiny like lights that on consoles or beacons or what have you, so not even enough to light up room or anything like that. That was fascinating. I really liked this video, and I really appreciate all the recommendations for this. I think they did a pretty good high-level showcase of what would happen. What if everyone jumped at once? That would involve a lot of very careful planning and coordination just to pull off. Don't think it would do much, but not sure, and I'm not sure why. Maybe some kind of charity event or something, but shouldn't affect the Earth very much. Let's see how wrong I am. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. See what this is all about.
From Thomas and many other people, who all asked, what would happen if everyone on Earth stood as close to each other as they could, jumped, and landed on the ground at the same instant?
Wow. Okay, so we're trying to get a whole bunch of people in one spot. A lot of people are going to die. And not from the effects of the jump, but just trying to get that many people into one spot like that. Throughout my training as a nuclear engineer in emergency response, one of the first things I learned was ordering an evacuation is not always the conservative option, because there's going to be panic, fear, especially when someone hears the word nuclear power plant. People are afraid of those because they don't understand how that works, and if there's an evacuation due to one of those, people are going to panic, or an evacuation due to anything, really. People are going to die probably in a car accident or whatever means of travel. The evacuation zones that I've had experiences working with were in towns and cities. This would be taken to the logical extreme of taking every person on Earth and placing them in one location. Now, even if we take into account that fear is not a motivator, but excitement about doing this jump, there's still just going to be that many logistical issues with coordinating travel, and not everyone's going to get there by car, but people are going to need some sort of vehicular transport to take part of the way. On the subject of car accidents, within the US anyway, according to the Department of Transportation, there's about 1 death per 100 million miles traveled. So let's just go out on a limb and say on average people are going to be traveling 1,000 miles to this one spot, which I know is an underestimate, but just to give a sense of scale, For 8 billion people, that figures out to 80,000 deaths. And this assumes normal travel, these congested amount of lanes and any other method of transit. I went with cars just because that's the deadliest form of travel. 80,000 casualties of just getting there. And that's just getting there, not going back home after the fact. You can see why this would be a horrific idea, just getting people in the same spot.
This is one of the most popular questions submitted to What If. It's been examined before, including by a Science Blogs post and a Straight Dope article. They cover the physics pretty well. However, they don't tell the whole story.
All right.
At the start of the scenario, the entirety of Earth's population has been magically transported together into one place.
So the wizardry saved well over 80,000 lives at this point. So I'm guessing we should only attempt this when we have magical powers.
This crowd takes up an area the size of Rhode Island. In fact, let's assume we, are actually in Rhode Island. At the stroke of noon, everyone jumps. As discussed elsewhere, this jump doesn't really affect the planet. Earth outweighs us by a factor of over 10 trillion. On average, we humans can vertically jump maybe half a meter, and that's when we're not shoulder to shoulder in the middle of a crowd. Even if everyone did jump that high, and the ground were rigid and responded instantly, the Earth would still only be pushed down by less than an atom's width.
The other thing is trying to get everyone to be in step. Man, that would be very difficult. I remember commenting on a lot of those videos about, hey, let's set off all nuclear weapons at once. Well, the problem is you set off one, it'll just destroy the ones next to it. One, contrary to popular belief and a lot of video game mechanics, is detonating one nuke, as in causing it to fission or induce fusion, depending on what type of bomb it is, would cause the other bombs to explode, and I mean explode using a nuclear reaction, not just as a result of the initial explosion, but to be kind of chained explosions. That's not really the case. Bombs are designed in such a way to only explode when it needs to, and when it is armed and when it is ready. So you'd have to arm them and detonate them in such a way so they would not actually engulf the other ones if you're going to maximize your destructive power. That being said, I also don't recommend nuclear disarmament being throw a bunch of nukes in a pile and just set one off. That's not the most environmentally friendly way to pull that off, though I'm sure some people have thought of that. So if you thought that was challenging with just hundreds to thousands of devices, here we're talking about billions of people. This is far enough away, even the distance over Rhode Island, that even if people could happen to respond immediately, the difference in the amount of time it takes from light to travel from one side of Rhode Island to the other would have a noticeable effect on the order of microseconds. This part's pretty hard to do as well.
Next, everyone falls back to the ground. Technically, this delivers a lot of energy into the Earth, but it's spread out over a large enough area that it doesn't do much more than leave footprints in a lot of gardens. A slight pulse of pressure spreads through the North American continental crust and dissipates with little effect beyond moving the needle of a few local seismometers.
Yeah, if everyone jumped, say, 0.3 meters simultaneously with a total mass of about 5 times 10 to the 11th kilograms, we'll get you something like 1.5 trillion joules, but joules are tiny, so we're talking around a 4 on the Richter scale. So enough for people to feel, although they'd probably feel the effects of their own jump more than anything else.
The sound of 12 billion feet hitting the ground does create a loud, drawn-out roar which lasts many seconds. Eventually, the air grows quiet. Seconds pass. Everyone looks around. There are a lot of uncomfortable glances. Someone coughs. A cell phone comes out of a pocket.
Oh, is he going to say this starts a pandemic? Okay.
Within seconds, the rest of the world's 7 billion phones follow. All of them, even those compatible with the region's towers, are displaying some version of no signal. The cell networks have all collapsed under the unprecedented load. Outside Rhode Island, abandoned machinery begins grinding to a halt. Airplanes drift through the skies on autopilot trajectories. Food starts burning on abandoned kitchen stove.
Oh, just because you teleported everyone into one spot, everything. Okay, and now we're getting into this scenario of what if everyone disappeared? How long would it take for the lights to burn out? I'll pin that one down in a comment below.
Soccer balls complete their trajectories into now vacant goals, and empty playground swings gradually drift to a halt. Back in Rhode Island, many people, begin to wonder, how do we get everyone home? The T.F. Green Airport in Warwick, Rhode
Yeah.
Island handles a few thousand passengers a day. I just flew out of there. They have the nicest bathrooms of any airport I've ever seen.
Yeah, that's just it. Who's going to drive everyone out and fly everyone home? And this is where all the deaths are going to occur. So you need to have the wizard to get people back.
Very impressive. This is not part of the recording. Assuming they got things organized, including sending out scouting missions to retrieve fuel, they could run at 500% capacity for 100 years without making a dent in the crowd. The addition of all the nearby airports doesn't change the equation much, nor does the region's light rail system. Crowds climb on board container ships in the deepwater port of Providence, but stocking sufficient food and water for a long sea voyage proves a challenge. Rhode Island's million cars are commandeered. Moments later, I-95, I-195, and I-295 become the sites of the largest traffic jams in the history of the planet. Most of the cars are blocked by the crowds, but a lucky few get out and begin wandering the
And this is basically the worst evacuation scenario now, because everyone has to evacuate where we're at. I had a feeling what I said earlier in the video was going to have a point, so here we are. I'm glad he's covering this. This is something that a lot of people don't realize about emergency response, and because this would certainly be an emergency.
abandoned road network. Some make it past New York or Boston before running out of fuel. Since the electricity is probably not on at this point, rather than finding a working gas pump, it's easier to just abandon the car and get in a new one. After all, who can stop you? All the cops are in Rhode Island.
Yeah, and we're assuming everyone knows how to commandeer a car. Well, people probably figure it out. Yeah, the infrastructure is not being manned at this point, so any little bit of grid instability event, and most power plants do require operator action. The grid requires operator action. Not all the time, but odds are by the time we get to the point where people have left Rhode Island, something happened, some weather phenomena probably caused some sort of disruption, and even relatively minor things do require grid operators. People forget, even with automated energy saver, smart grid technology, still need operators. AI has not taken away the job of grid operators or power plant operators yet. And especially in the case of nuclear power plants, I don't see that happening anytime in the near future, just because not a whole lot of people trust nuclear power plants to be manned by AI, at least in terms of decision making. The closest I see AI in nuclear power plants would be in providing input and recommendations, but a person, and by a person I mean a licensed senior reactor operator, is going to be the decision maker, because they have the expertise and the training. And it's a lot. I've been through that program. It was well over 2 years after getting my nuclear engineering degree.
The edge of the crowd spreads outward into southern Massachusetts and Connecticut. Any two people who meet are unlikely to have a language in common, and almost nobody knows the area. Even if people cooperate, everyone is hungry and
because population of Rhode Island's about 1 million, so divide that through by 8 billion, you have a 1 in 8 million chance that someone knows where they are. Wow.
thirsty. Grocery stores are immediately emptied and woefully insufficient. Fresh water is hard to come by, and there's no efficient system for distributing it. Sanitation is a disaster, and healthcare infrastructure non-existent. Within weeks, Rhode Island is a graveyard of billions, including most of the people who submitted this question, probably you and me too.
Yeah, odds are. I wonder how many people submitted this question.
The survivors spread out over the face of the world and struggle to build a new civilization atop the ruins of the old. Our species staggers on, but our population has been greatly reduced. And, most importantly, the Earth's rotation and orbit are completely unaffected. So
this had a far more devastating impact with the use of magic, and the problem was it was one-way magic. Whereas if everyone, coordinated and knew how to get there, then presumably with the consequences would have been less. Though, actually maybe not. The goal is to still get 8 billion people there, not 6 billion or 7 billion. Say leave 1 billion behind to manage all the critical infrastructure. Then everyone would get there, but you'd still run into the same issue. So, all right. I stand corrected on this whole assessment. Turns out it's way worse than I initially thought. That's fascinating. So you have to have two-way magic. Lesson learned. It spins along exactly as it did before our species-wide jump. Note to future civilizations. Let's not try that again. I like this. They completely turned what would be a pretty simple physics problem that I'm sure people have seen a variant of it on some physics test in high school where you get like where they give you a few rough assumptions and then just kind of put it on there for grins. But the tragic blend of putting some realism into the fantasy of this scenario, and this is what this channel does best. That was a great one, the twist ending, and crazy how I underestimated how bad this would be. Still a very fun video. Could you make an umbrella out of lasers? Well, the question is phrased, could you? And the answer is, yeah, probably, but it would be a very expensive umbrella, and I don't think the FAA would appreciate it too much. I know at a nuclear power plant, you have to notify them whenever the flashing lights on top of the reactor containment building domes are burnt out. So shooting a massive laser up into the sky, yeah, they probably wouldn't appreciate that too much. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's check out this craziness.
From Zach, who asks, stopping rain from falling on something with an umbrella is boring. What if you tried to stop rain with a laser that targeted and vaporized each incoming droplet before it could come within 10 feet of the ground?
Now that's an interesting idea. Let's just go ahead and target the cloud, at least according to this diagram. Go ahead and punch a hole through that thing that's dropping all the rain on you. I'm sure that's not going to have any adverse weather consequences.
So, stopping rain with a laser is one of those ideas that sounds totally reasonable, but... well, okay. While the idea of a laser umbrella might be appealing, okay, the idea of stopping rain with a laser is a thing we are currently talking about. Now, it's not a very practical idea. First, let's look at how much energy the laser would need. Vaporizing a liter of water takes about 2.6 megajoules of energy, and a big rainstorm might drop half an inch of rain per hour. Oddly enough, you can just multiply these two numbers together in a smart calculator like Wolfram Alpha or
I love Wolfram Alpha.
or Google, and the units work out to give you an answer in terms of power per surface area, which is exactly what we're looking for. The calculator...
Yeah, that's a lot. So in nuclear power plants, you look at power density like this, so power per unit area or even per linear foot. That's one of the things you look at when you're designing a reactor core. And what's really important about this is you want it to be relatively even throughout the core. You don't want hot spots because that's just going to make temperature distribution in the reactor get off. More of the fuel's going to burn up faster. It's a less efficient process. It's also less uniform, and a safe, efficient power plant needs relatively uniform energy density. So we regularly look at kilowatts per linear foot or kilowatts per square foot because I work in an American nuclear power plant. So kilowatts per meter squared or per centimeter squared, you would obviously see those in countries that use the metric system.
Says that we need 9 kilowatts of power per square meter we want to protect with our laser. 9 kilowatts per square meter is nearly 10 times the amount of power Earth's surface receives from the sun. And while that sounds like a lot of energy,
so you can't do this with solar.
we need to remember that water's capacity to absorb energy is incredible. Heating water up to boiling only takes about 10% of the energy. Getting it from liquid to gas takes the other 90%. Ultimately, we're talking about filling the air with tons of hot steam. So basically, we'd be building a human-sized autoclave. Needless to say, autoclaves are not really a popular place to live. But
one other way of looking at this is if you hooked this laser up to a nuclear power plant, and when I say that, you just somehow hooked it up right to the main generator. So I'm going to go ahead and make it simple and neglect transmission line losses at this point that you would need to step this down to an appropriate voltage for using a handheld device like this. At 10 kilowatts per square meter, I'm going to go ahead and round up just because that's an easier number to work with. And I'm going to assume you have 1 gigawatt coming out of the reactor's main turbine. That figures out to only 100,000 square meters, or 0.1 square kilometer. So the entire might of a nuclear power plant isn't even protecting you from that much rain. And I'm also assuming this laser thing has the right lens configuration and beam expanders, plus the ability to adjust its pitch depending on which direction the rain's coming from. Because as someone who lives in Texas, I'm quite used to it raining sideways. So not exactly the most efficient way to use a nuclear power plant.
It's worse. Vaporizing a droplet of water with a laser is more complicated than it sounds. There are many, many, many papers on this subject, and the general gist is that it takes a lot of energy delivered fast to vaporize the droplet without just splattering it apart into little droplets. Here's what it looks like when a droplet gets zapped by a laser pulse. You can see that I'm jealous of anyone whose job it is to literally zap water with lasers.
That's true, because it's just gonna, good luck focusing it in that it's this uniform destruction, imparting all that energy to completely taking it out. You'd have to surround it. You'd have to somehow surround the individual droplet like you're trying to start a fusion reaction in inertial confinement style, which good luck trying to pull something like that off with raindrops.
You can also see that the laser mostly splatters the droplet rather than vaporizing it. The implication is that completely vaporizing a droplet would probably take even more than the already unreasonable amount of power we were considering.
Maybe this will be one of the uses for nuclear fusion, specifically inertial confinement fusion, if anyone can figure that out.
Then there's the problem of targeting and aiming. In theory, this is probably solvable, perhaps even without military-grade equipment. High-speed cameras can triangulate the 3D position of a baseball or football hundreds of times per second to help referees make calls. A similar but more sophisticated system could help track the incoming raindrops.
I like how they're just kind of showing them hanging up there, presumably attached to the cloud, like this is in Super Mario World or something.
As for targeting, adaptive optics allows for extremely fast and precise control of beams of light. Covering an area of a square meter would require something like 500 direct pulses of light per second. This is slow enough that you wouldn't run into any direct problems with relativity, but the device would, at minimum, need to be a lot more complicated than just a laser pointer on a swiveling base.
So, why isn't he just splitting it into like an expander to just make it over a much larger area? I mean, it wouldn't be instant, it would be kind of like while the individual droplet is falling. Maybe he is. This might just be the graphics of showing what this looks like, because it would be a bit harder to read if he showed it aiming upward. I probably shouldn't take this too seriously.
It might seem easier to forget about targeting completely and just fire lasers in random directions. If you aim a laser beam in a random direction, how far will it go before it hits a drop? This is a pretty easy question to answer. It's the same as asking how far you can see in the rain, and the answer is at least several hundred meters. So unless you're trying to protect your whole neighborhood, firing powerful lasers in random directions probably won't help.
Trying to protect your neighborhood, yeah, you might hit people. And also, a beam that would be this powerful, man, this would be like well beyond class 4 lasers. Maybe Styropyro is going to try something like this at some point, but people around anywhere near this thing is going to need to have the right level of eye protection and just the heat protection, because this is connected right to some sort of magical power plant. That little box with the lightning bolt in there is basically a micro reactor, and I say micro reactor in that it's small, but we're talking a full-size nuclear power plant if you're going to be even affecting something greater than 0.1 square kilometers. So yeah, the point is your neighbors aren't going to like this, even if you don't hit them in the face with a laser. Even seeing like a reflection of that beam off of a droplet is going to be enough to cause severe eye damage, possibly permanent blindness, depending on how close you are to the thing.
And honestly, if you are trying to protect your whole neighborhood, firing powerful lasers in random directions definitely won't help.
Oh, I'd love to see someone try to get that past their HOA. Though I don't see why, again, you use just lens expanders and aim it straight up, though. That would probably have less of this effect, though the FAA is still not going to like you, pilots aren't going to like you, and really anyone standing close to the beam, but that would probably minimize this sort of effect, though the fires could still be there depending on how much heat your magical generator is producing. So yeah, if that's the case, then you're probably not going to want the rain to go away. The rain might be the one thing preventing the fire from spreading. That was crazy. And I think this probably gave Styropyro another idea if he hasn't thought of one already. What if you threw a baseball at nearly light speed, and here it's showing 90% the speed of light? Just in terms of kinetic energy, that should be comparable to a pretty good-sized nuclear explosion. Those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's check this out.
This question comes from Ellen, who asks, what would happen if you tried to hit a baseball pitched at 90% the speed of light?
Oh, if you tried to hit one. Wow. That one, you're probably better off not swinging at it. Especially because you wouldn't want to be anywhere near this thing.
Let's set aside the question of how we got the baseball moving that fast. We'll suppose that it's a normal pitch, except in the instant the pitcher releases the ball, it magically accelerates to 0.9 c.
There you go. A wizard did it. Yeah, good luck accelerating something like this in some sort of particle accelerator, especially considering this. You'd have to put super magnets on it and accelerate around your cyclotron, but something this size would fall apart long before you even get this fast. So, yeah, I'm glad we're shifting to using wizardry right away. Otherwise, you'd never get there. Kind of like in one of their previous videos of how they got the submarine into space to begin with. But no, nobody's accelerated anything that big in any particle accelerator. It's just, things just aren't going to be in one piece at anywhere close to that speed that are that large. The mass of a baseball, or I guess I should say the rest mass of a baseball, since we're dealing with relativistic things, is about 0.145 kilograms.
From that point onward, everything proceeds according to normal physics. And what proceeds turns out to be a lot of things. And they all happen very quickly, and it doesn't end well for the batter, or the pitcher. What follows,
or anyone watching the game, or anyone in the city that the game is being watched.
is my best guess at a nanosecond by nanosecond portrait. The ball is going so fast that everything else is practically stationary. Even the molecules in the air are stationary.
Yeah, that is just the kinetic theory of gases, of just air at normal, I'm gonna say it's normal 80 degrees and sunny, but limited humidity sort of temperature. So even the most delicate of pitchers that treat their arms like they're orchids, would be good pitching in these conditions. If you're a baseball fan, I bet you have a few people in mind that I'm talking about that can only pitch under the best conditions possible. But the point is, even the best pitching conditions possible for this particular scenario, it's not even gonna matter. Extreme heating, ionization of the air. This thing is going to be a fireball, assuming it somehow maintains its shape. Could just be like what looks like a beam of energy, kind of like in Dragon Ball when they throw an energy ball or something like that. This will be my only attempt trying to use real physics on Dragon Ball.
Air molecules vibrate back and forth at a few hundred miles per hour, but the ball is moving through them at 600 million miles per hour. This means that as far as the ball is concerned, they're just hanging there frozen. The ideas of aerodynamics don't apply here. Normally, air would flow around anything moving through it, but the air molecules in front of this ball don't have time to be jostled out of the way.
Yeah, aerodynamics, yeah, we're dealing with extreme ballistics at this point. And by extreme ballistics, I mean ones that are similar to, say, an asteroid impact. Missiles don't go this fast. Nuclear bombs, as far as the bomb traveling, doesn't behave like this. An explosion would occur pretty quickly in that a massive shockwave would be sent out. I mean, we're talking like a large nuclear weapon. At 90%, that figures out to about 4 megatons. Granted, that's not the largest nuclear weapon ever, but it's pretty far up there. It's about 10 times more than the average strategic nuclear weapon. It's still over 12 times smaller than the largest nuclear weapon, the Tsar Bomba, but that was a ridiculous, impractical weapon, kind of, and only slightly more anchored in reality than this experiment right here.
The ball smacks into them so hard that the atomic nuclei in the air molecules actually fuse with the atomic nuclei in the ball.
So he mentions fusion. I don't think so. So it is going to create high pressure and high temperature, very much so, locally, but it's not going to be in one spot. There's no confinement zone to sustain a fusion reaction. Hello, this is future Tyler here. Yeah, past Tyler, I think you got your head a little too wrapped around the whole self-sustaining fusion reaction aspect of this. Atoms are being combined, so I think you were a little misleading there, past Tyler. This would be closer to a particle accelerator reaction than one found in a fusion reactor. Thank you very much for all of your comments on this matter. I really appreciate it, and I didn't want to confuse anyone by saying this. This is the first time I've ever reacted to one of my own videos. This feels weird. Maybe I'll do this again sometime.
Each collision releases a burst of gamma rays and scattered subatomic particles. These gamma rays and debris expand outward in a bubble centered around the pitcher's
Disintegrating pitcher, unsuspecting batter.
They start to tear apart the molecules in the air, ripping electrons from nuclei and turning the air in the stadium into an expanding bubble of incandescent plasma.
What's crazy is, considering how fast this is, it's not going to register on the batter's eyeballs that the pitcher isn't there anymore and before it's too late, because he's saying 60 nanoseconds. Or as I like to call it, 6 shakes, because one shake is 10 nanoseconds. A weird nuclear engineering unit describing the speed of nuclear reactions. It was all in code because everything else was in code during the Manhattan Project. So 6 shakes. Good luck hitting this thing.
The surface of the bubble approaches the batter at about the speed of light, only slightly ahead of the ball itself. The constant fusion at the front of the ball pushes back on it, slowing it down, as if the ball were a rocket flying tail first while firing nuclear fusion engines. Unfortunately, the ball is going so fast that even the tremendous force from this ongoing thermonuclear explosion barely slows it down at all.
Now, his use of the word thermonuclear, I guess that's technically right, because high temperature is occurring and nuclear reactions are occurring. It doesn't have to be fusion, even though a thermonuclear weapon is usually associated with a powerful nuclear bomb that involves a fusion state. Interesting. Don't often hear the words thermonuclear come up with baseball, but here we are.
It does, however, start to eat away at the surface, blasting tiny particulate fragments of the ball in all directions.
I'm kind of surprised the ball is still in one piece at, what are we up to, 6 shakes at this point? Maybe. It doesn't look like that. It's a plasma ball or fireball at this point.
These fragments are going so fast that when they hit air molecules, they trigger 2 or 3 more rounds of fusion. After about 60 nanoseconds,
He's using the word fusion when he means spillations.
the shell of X-rays arrives at home plate, and a handful of nanoseconds later, the ball hits. The
0.3 more shakes. Oh, man.
batter hasn't even seen the pitcher let go of the ball, since the light carrying that information arrives at about the same time as the shockwave.
Yeah, the batter and pitcher are both gone, but that's not even the worst part of this. The worst part of this is this is going to count as a hit, because he was effectively hit by the pitch, and he's going to get on base, or I guess I should say what's left of the batter is going to get on what's left of base. And considering the yield of this thing is about 4 megatons, the baseball stadium and surrounding area, not much. But as far as the rules of baseball, this isn't a recommended strategy either, just for playing the game.
Collisions with the air have eaten the ball away almost completely, and it is now a bullet-shaped cloud of expanding plasma, mainly carbon, oxygen, hydrogen, and nitrogen.
Wow, a lot happened in that 3/10 of a shake. Cool.
Ramming into the air and triggering more fusion as it goes. When it reaches the batter,
I do have a bit of a problem with him referring to it as fusion, because it's not, I mean, it's high energy collisions, but this is not at all the same type of fusion that happens in a fusion reactor, a star, or a nuclear bomb. But considering how this is going to have the destructive power of a strong nuclear bomb.
the center of the cloud is still moving at an appreciable fraction of the speed of light. It hits the bat first, but then the batter, plate, and catcher are all scooped up and carried backward through the backstop as they
Oh, got rid of the umpire too. I'm glad they even referred to the umpire. Unsuspecting backstop.
disintegrate. The shell of X-rays and superheated plasma expands outward and upwards, swallowing the backstop, both teams, the stands, and
Yeah, 40 shakes. This is all within the fireball. So a 4 megaton surface detonation. I'm gonna call this a surface detonation because it's barely off the ground at this point. So here it is using NukeMap, which is a great free resource by Alex Wellerstein. I will put the link to this in the description. This is a 4,000 kiloton surface detonation, going with Washington, D.C., as tribute to a certain Washington Nationals starting pitcher that I always thought was a bit of an orchid, in that weather conditions had to be just right for him to be good in the game. So yeah, that yellow radius, the fireball, is 2.44 kilometers of immediately destroyed. The green's the radiation at 500 rem dose, which is likely lethal within a month, though these people aren't going to last a month because The red radius is the 20 psi shockwave, and everything is shattered and destroyed within that 3.45 kilometers. Moderate blast, 5 psi, is the gray circle where most buildings are going to be destroyed at 7.27 kilometers. And that big orange one is 19.4 kilometers radius. Everything there is going to get a third-degree burn. Now that's what a 4,000 kiloton nuclear weapon would do. This is going to be more targeted in that it's going to cause more of an effect of everything in that particular direction that it's going. So it's going to be a slightly different shape, and it's going to be more oblong or elliptical than circular, but this should still give a general sense of the size of the affected area.
The surrounding neighborhood, all in the first microsecond. Suppose you're watching from a hilltop outside the city. The first thing you see is a blinding flash far outshining the sun.
Yep.
This gradually fades over the course of a few seconds, and a growing fireball rises into a mushroom cloud. Then, with a great roar, the blast wave arrives, tearing up trees and shredding houses.
Yep, if you're just a few kilometers away, it's not going to be good for you.
Everything within roughly a mile of the park is leveled, and a firestorm engulfs the surrounding city. The baseball diamond is now a sizable crater centered a few hundred feet behind the former location of the backstop.
Yeah, more than a mile even.
A careful reading of official Major League Baseball Rule 5.05b2 suggests that in this situation, the batter would be considered hit by pitch.
Yep, that's exactly what I thought.
And would be eligible to advance to first base.
That's the best part right there, isn't it? So, a very expensive and destructive and needlessly destructive way to walk someone, assuming we had access to whatever wizard's powers that gave us the ability to do that. I really enjoyed this video. Thank you so much for the recommendation, and thank you for watching. I'll see you next time.